Welcome to Scientific Discovery Hub, where we unravel the mysteries of the cosmos. Have you ever wondered about the origins of the universe? What if I told you there's a faint glow of light left over from 13.8 billion years ago that holds the secrets to everything we see today? That's the story we are diving into. In this video, we'll explore the cosmic microwave background, CMB, the oldest light in the universe, and how it acts as a cosmic time machine, revealing the universe's birth, evolution, and even its mysterious components like dark matter and dark energy. Imagine a baby picture of the universe, a snapshot from just 380,000 years after the Big Bang. That's the CMB. It's like a fossilized echo of the Big Bang, imprinted with tiny temperature fluctuations that seeded the formation of galaxies, stars, and ultimately life itself. But how did this light come to be? Why is it uniform across the sky? And what strange anomalies hide within its data? We'll break it all down. Here's what we'll cover: the Big Bang's afterglow, how the CMB proves our universe exploded into existence, and how quantum ripples became galaxies; cosmic inflation, a mind-bending theory where the universe expanded faster than light, solving puzzles about its uniformity; dark matter and dark energy, why 95% of the universe is invisible, and how the CMB exposes their cosmic dominance; weird CMB anomalies, like the infamous cold spot, a possible hint of a multiverse; satellites that changed science. From COBE to Planck, how missions map the CMB and revolutionize cosmology; future discoveries, what upcoming tech could unlock secrets of the universe's first billion years. Whether you're a curious stargazer or a science enthusiast, this video will take you on a journey through time and space, blending cutting-edge research with mind-expanding ideas. No PhD needed, just curiosity. Along the way, we'll tackle questions like, why does the universe look the same in every direction? Could there be other universes beyond our own? And what lies beyond the CMB's cosmic fog? Hit play to dive into the science behind the universe's first light. And don't forget to like, subscribe, and join our community as we explore the wonders of the cosmos. Let's decode the universe together. In the vast expanse of the cosmos, where stars are born and die in silent, cataclysmic dances, there exists a quiet, omnipresent hum. It is not the roar of supernovae, nor the crackle of quasars, but a faint, almost imperceptible murmur that stretches across the fabric of space-time itself. This is the cosmic microwave background, CMB, a relic of the universe's earliest moments, a ghostly echo of the Big Bang that reverberates through the void. Imagine a lullaby sung by the universe to itself, a song so ancient that its notes have been stretched and softened by the passage of eons. Yet, for those who dare to listen, the CMB offers a window into the primordial chaos from which all things emerged. It is a cosmic fingerprint, imprinted with the delicate imbalances that seeded the galaxies, the stars, and ultimately, the life that now contemplates them. To study the CMB is to peer into the womb of creation, where the seeds of our existence were sown in the heat of a newborn universe. But how does one hear the voice of time itself? The answer lies in the interplay of light and darkness, of fire and silence. In the first fraction of a second after the Big Bang, the universe was a seething cauldron of energy too hot for even the simplest particles to form. Photons, the messengers of light, were trapped in a relentless dance with electrons and protons, their paths scattered endlessly in a dense plasma. This opaque soup, glowing with the fury of a trillion suns, could not yet carry information across space. It was only after 380,000 years, a blink in cosmic terms, that the universe cooled sufficiently for electrons and protons to combine into neutral hydrogen atoms. This moment, known as recombination, marked the end of the cosmic dark age and the birth of the first free photons. These photons, once liberated, began their journey across the expanding universe, their wavelengths gradually stretched by the very expansion they traversed. What was once a brilliant flash of visible light has since become a faint glow of microwaves, undetectable to human eyes, but unmistakable to the instruments of modern astronomy. The CMB is not merely a relic, it is a treasure trove of cosmic history. Its temperature variations, measured in millionths of a degree, reveal the intricate story of the universe's infancy. These minuscule fluctuations, regions slightly warmer or cooler than their neighbors, are the seeds of all structure. They are the ripples in the cosmic ocean, the gravitational blueprints that guided the formation of galaxies and clusters. By mapping these variations, scientists have confirmed the Big Bang theory with extraordinary precision, measured the age of the universe to within a few 100 million years, and even glimpsed the mysterious forces that govern its expansion, dark matter and dark energy. The CMB is both a testament to the power of human ingenuity and a humbling reminder of how much remains beyond our grasp. Yet, for all its revelations, the CMB also poses profound questions. Why is the universe so uniformly smooth, with only the tiniest deviations from perfect equilibrium? How did such minute fluctuations grow into the vast cosmic web we observe today? And what lies beyond the veil of the observable universe, in the uncharted territories where light has never reached? These enigmas compel us to refine our theories, to push the boundaries of observation, and to confront the limits of our understanding. The CMB is not just a relic of the past, it is a beacon guiding us toward the unknown, a silent invitation to unravel the mysteries of the cosmos. As we stand beneath the night sky, gazing at the distant glimmers of stars and the faint glow of the Milky Way, we are surrounded by echoes of the CMB. It permeates every corner of existence, a constant invisible presence that binds us to the universe's earliest moments. In this quiet resonance, we find a connection not only to the stars but to the fundamental forces that shape reality itself. The CMB reminds us that we are not mere spectators of the cosmos. We are its children, born from the same primordial fire, our stories etched into the very fabric of the universe. To decode this echo, we must rewind the cosmic clock. Peering back to the instant of creation, the Big Bang was not a singular event, but a process, a sequence of transformations that unfolded in unimaginable speed and scale. Before the first moment, there was no time, no space, no matter, only a singularity of infinite density and temperature. From this point of pure potential, the universe burst forth in an inflationary surge, expanding faster than the speed of light, stretching the fabric of space-time itself. In this explosive beginning, the laws of physics as we know them were rewritten, and the seeds of the CMB were sown. To understand the CMB is to understand the universe's first breath, the moment when the cosmos began its eternal journey from chaos to order. The study of the CMB is a testament to the resilience of curiosity and the power of technology. From the accidental discovery by Arno Penzias and Robert Wilson in 1965 to the precise measurements of the Planck satellite, each step forward has brought us closer to the truth. Yet, for all we have learned, the CMB remains a source of wonder, a reminder that the universe is both comprehensible and infinitely complex. It challenges us to reconcile the quantum realm with the macroscopic world, to grapple with the paradoxes of time and space, and to imagine what may lie beyond the veil of the observable. In the CMB, we find not just the echoes of the past, but the questions that will propel us into the future. As we continue our exploration, let us carry with us the humility of knowing that the universe is vast, its secrets countless. The CMB is more than a scientific phenomenon. It is a symbol of our shared quest for knowledge, a bridge between the ancient and the eternal. In its quiet glow, we are reminded that the universe is not a static entity, but a living, evolving story, one in which we are both participants and seekers. And so, with the CMB as our guide, we take the next step in our journey, venturing into the heart of the Big Bang itself, where the first sparks of creation ignited the cosmos. To rewind to the moment of the Big Bang is to enter a realm where the familiar laws of physics dissolve into abstraction. Picture a singularity, a point of infinite density and temperature, where time and space as we know them cease to exist. This is not a location in the conventional sense, but a conceptual boundary, a starting point for the universe's expansion. Around 13.8 billion years ago, this singularity underwent an explosive release of energy, a rapid inflation that stretched the fabric of space-time itself. In an infinitesimal fraction of a second, the universe expanded exponentially, growing from a subatomic speck to a size larger than the observable universe we see today. This inflationary epoch, driven by a mysterious force now referred to as the inflaton field, smoothed out irregularities and set the stage for the cosmic structure we observe in the CMB. During this initial phase, the universe was governed by the four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. But these forces were unified in a single, all-encompassing interaction. As the universe expanded and cooled, it underwent a series of phase transitions, much like water freezing into ice or boiling into steam. These transitions broke the symmetry of the unified forces, giving rise to the distinct interactions we recognize today. The first of these transitions separated gravity from the other forces, followed by the splitting of the electro-weak force into electricity and magnetism. These events, occurring within the first nanosecond of the universe's existence, laid the foundation for the particles and forces that would later shape the cosmos. By the time the universe was a millisecond old, it had already undergone a dramatic transformation. Quarks and gluons, the building blocks of protons and neutrons, swirled in a dense quark-gluon plasma, their interactions governed by the strong nuclear force. The temperature was still a staggering 10-15 degrees Celsius, hotter than the cores of the most massive stars. As the universe continued to expand, it cooled further, allowing quarks to combine into protons and neutrons. This period, known as the quark epoch, marked the emergence of the first stable particles, though the universe remained a hostile environment, filled with high-energy photons and neutrinos. The next critical milestone came when the universe was about 3 minutes old. By this time, the temperature had dropped to approximately 1 billion degrees Celsius, allowing protons and neutrons to fuse into the nuclei of light elements. This nucleosynthesis period gave rise to helium, deuterium, and trace amounts of lithium and beryllium, the building blocks of the first stars. The abundance of these elements, measured in the present-day universe, provides a crucial test for Big Bang theory. The observed ratios of hydrogen to helium match predictions with remarkable precision, offering indirect evidence for the conditions of the early universe. However, the universe was still far from being a place where atoms could form. For the next 380,000 years, the cosmos remained a seething plasma, with photons constantly colliding with free electrons and protons. This dense, ionized medium prevented light from traveling freely, rendering the universe opaque. During this era, the universe was essentially a featureless, glowing fog, its photons trapped in an endless cycle of absorption and emission. It was only when the temperature fell below 3,000 degrees Celsius that electrons and protons could finally combine to form neutral hydrogen atoms. This moment, known as recombination, marked the end of the cosmic dark age and the birth of the first free photons. The photons released during recombination began their long journey through space, their wavelengths gradually stretched by the universe's expansion. What was once a blinding flash of visible light became a faint, cold glow of microwaves, detectable today as the cosmic microwave background. The CMB is thus a direct snapshot of the universe at this pivotal moment, a relic of the first light ever to travel unimpeded. The tiny temperature fluctuations in the CMB, measured in microkelvins, correspond to the density variations in the early universe, regions where matter was slightly denser or less dense. These fluctuations, amplified by gravity over billions of years, eventually collapsed under their own weight to form the first stars, galaxies, and the vast cosmic web we see today. The study of the Big Bang is not merely an exercise in reconstructing the past. It is a lens through which we examine the fundamental nature of reality, the extreme conditions of the early universe, where temperatures and energies were higher than anything achievable in terrestrial laboratories, provide insights into the behavior of matter and energy under extreme conditions. For instance, the detection of gravitational waves, ripples in spacetime predicted by Einstein's theory of general relativity, offers a new way to probe the universe's infancy. If such waves were generated during the inflationary epoch, they might leave an imprint on the polarization of the CMB, providing direct evidence for the mechanism that drove the universe's rapid expansion. Moreover, the Big Bang theory raises profound questions about the origins of the universe itself. What triggered the initial singularity? Was there a prior state to the universe? Or did time and space emerge from nothingness? These questions lie at the intersection of cosmology and quantum mechanics, two fields that remain stubbornly incompatible. The search for a theory of quantum gravity, a framework that unifies general relativity with quantum field theory, may hold the key to understanding the universe's birth. Concepts such as the multiverse, where our universe is just one of many in a vast cosmic landscape, or the idea of a cyclic universe that expands and contracts in an eternal rhythm, offer tantalizing possibilities. Yet, without experimental evidence, these ideas remain speculative, leaving us with more questions than answers. The Big Bang is not a singular event, but a continuum of processes, a chain of causality that links the universe's earliest moments to its present-day complexity. From the inflationary surge that smoothed out the cosmos to the nucleosynthesis that forged the first elements, each phase of the Big Bang's unfolding story contributed to the universe we inhabit today. The CMB, with its intricate patterns of temperature variation, serves as a Rosetta Stone for decoding this history, a map of the universe's genetic code. By studying the CMB in exquisite detail, scientists have determined the universe's age, composition, and geometry with unprecedented accuracy. They have confirmed that ordinary matter constitutes less than 5% of the cosmos, with the rest composed of dark matter, about 27%, and dark energy, approximately 68%. These mysterious components, whose true nature remains elusive, dominate the universe's structure and expansion, shaping its fate in ways we are only beginning to comprehend. The Big Bang is a story of extremes, of infinite density, of blistering heat, of forces that defied separation. Yet, from this primordial chaos emerged the delicate balance that allows galaxies to form, stars to shine, and planets to harbor life. The CMB is a reminder that the universe is not static, but dynamic, evolving according to the interplay of gravity, entropy, and the fundamental constants of nature. It is a story of transformation, from the singularity of the Big Bang to the vast, expanding cosmos we observe today. And as we continue to probe the depths of the CMB and the mysteries of the early universe, we are not merely uncovering the past, we are shaping the future of our understanding, inching closer to the ultimate question: what is the nature of reality itself? The cosmic microwave background, CMB, is more than a relic of the past. It is a cosmic blueprint, a map of the universe's genetic code. Every fluctuation in its temperature, every subtle variation in its intensity, tells a story of the forces that have shaped existence. These fluctuations, though seemingly random, are the result of quantum fluctuations magnified by the universe's rapid expansion during the inflationary epoch. These quantum ripples, frozen into the fabric of space-time, became the seeds of all structure, galaxies, stars, and even the superclusters that span billions of light years. By studying the CMB, scientists can trace the evolution of the universe from its earliest moments to the present day, reconstructing the history of matter and energy with astonishing precision. One of the most profound insights gleaned from the CMB is the confirmation of the Big Bang theory. The uniformity of the CMB across the sky, with temperature variations no greater than 1/1000th of a degree, suggests that the universe was once in thermal equilibrium. However, this uniformity poses a challenge. If the universe expanded rapidly, how could regions that are now separated by vast distances have interacted to achieve such homogeneity? This conundrum, known as the horizon problem, led to the development of the inflationary model. According to this theory, the universe underwent an exponential expansion in its first fraction of a second, smoothing out irregularities and setting the stage for the CMB's near-perfect uniformity. The CMB's anisotropies, the tiny temperature differences, provide direct evidence for this inflationary period, confirming the model's predictions with remarkable accuracy. Beyond confirming the Big Bang, the CMB offers a unique window into the nature of dark matter and dark energy, the two most enigmatic components of the universe. While dark matter cannot be seen directly, its gravitational influence is evident in the way galaxies rotate and cluster together. The CMB data reveals that dark matter constitutes about 27% of the universe's total mass energy content, While ordinary matter accounts for less than 5%, the remaining 68% is attributed to dark energy, a mysterious force driving the universe's accelerated expansion. The CMB's fluctuations are sensitive to the distribution of dark matter, as gravitational interactions between dark matter and ordinary matter shape the large-scale structure of the universe. By analyzing these fluctuations, scientists can infer the properties of dark matter and its role in the cosmic web. Similarly, the CMB provides constraints on the equation of state of dark energy, helping to determine whether it behaves as a constant, as in Einstein's cosmological constant, or if it evolves over time. The CMB also sheds light on the geometry of the universe, revealing that it is spatially flat on large scales. This finding aligns with the predictions of inflationary theory, which posits that the universe's rapid expansion flattened any curvature. Much like inflating a balloon smooths out its surface, the flatness of the universe has profound implications for its ultimate fate. In a flat universe, the expansion will continue indefinitely, albeit at an accelerating rate, due to dark energy. This means that galaxies will drift apart from one another, eventually becoming isolated islands in an ever-expanding void. The CMB's data supports this scenario, reinforcing the notion that the universe is destined for a cold, lonely end. Despite the wealth of knowledge extracted from the CMB, many questions remain unanswered. One of the greatest mysteries is the nature of dark matter and dark energy themselves. What are the fundamental particles that constitute dark matter, and how do they interact with ordinary matter? Is dark energy a static property of space-time, or does it change over time? These questions lie at the forefront of modern astrophysics and particle physics, driving experiments such as the Large Hadron Collider and the upcoming James Webb Space Telescope. The CMB serves as a benchmark for these investigations, providing constraints that guide theoretical models and experimental designs. Another area of active research is the search for primordial gravitational waves, ripples in space-time predicted by inflationary theory. These waves, if detected, would offer direct evidence for the inflationary epoch and provide insight into the energy scale at which inflation occurred. The CMB's polarization patterns, particularly the B-mode polarization, are a promising avenue for detecting these gravitational waves. While earlier attempts, such as the BICEP-2 experiment in 2014, yielded inconclusive results due to foreground contamination from galactic dust, future missions like the Simons Observatory and the Lightbird satellite aim to overcome these challenges with improved sensitivity and resolution. The discovery of primordial gravitational waves would be a monumental achievement, bridging the gap between cosmology and quantum gravity. The CMB also plays a crucial role in testing alternative theories of gravity and the early universe. For example, modified gravity models, which propose deviations from Einstein's general relativity, can be constrained by comparing their predictions with the CMB's observed features. Similarly, theories involving extra dimensions or cyclic universes must account for the CMB's anisotropies and the universe's overall geometry. These tests not only refine our understanding of gravity, but also open the door to new physics beyond the standard model of particle physics. Perhaps the most profound implication of the CMB is its role in our quest to understand the universe's origins. The fact that we can observe the CMB at all is a testament to the universe's transparency after recombination, a moment when the first light was freed to traverse the cosmos. This light carries with it the imprints of the universe's earliest moments, a record of the conditions that existed 13.8 billion years ago. In a sense, the CMB is a message from the universe to itself, a cosmic diary that spans the entire history of time. To study the CMB is to engage in a dialogue with the past, a conversation that transcends the boundaries of space and time. As we continue to probe the CMB with increasingly sophisticated instruments, we are not only refining our existing models, but also uncovering new phenomena that challenge our understanding. For instance, recent analyses of the CMB have revealed anomalies in its temperature fluctuations, such as the so-called cold spot, a region larger than expected that deviates significantly from the average temperature. These anomalies, though statistically marginal, suggest that there may be aspects of the universe's structure that remain unexplained. Some researchers propose that these features could be the result of cosmic defects, such as cosmic strings or textures, remnants of phase transitions in the early universe. Others speculate that they may be signatures of a multiverse, where our universe is just one of many in a vast ensemble of realities. While these ideas are highly speculative, they illustrate the boundless potential of the CMB to inspire new lines of inquiry. In the grand tapestry of the cosmos, the CMB stands as a luminous thread, weaving together the threads of time, space, and matter. It is a testament to the universe's ability to preserve its history in the faintest whispers of light, a reminder that even the most distant past is not lost, but encoded in the fabric of the present. The study of the CMB is not merely an academic pursuit. It is a journey of discovery, a voyage into the heart of the cosmos to unravel the secrets of our existence. With each new measurement, each new insight, we come closer to understanding the universe's grand design, and perhaps in doing so, we come closer to understanding ourselves. As we stand at the precipice of knowledge, gazing into the abyss of the unknown, the cosmic microwave background, CMB, emerges as both a compass and a mirror. It reflects the universe's earliest moments, while pointing toward the frontiers of our comprehension. The CMB is a bridge between the tangible and the theoretical, a nexus where the empirical rigor of observation meets the boundless speculation of human imagination. Its study is not merely an exercise in charting the past, but a catalyst for envisioning the future of cosmology, a discipline poised to answer questions that have perplexed thinkers for millennia. The CMB's role in probing the universe's geometry and composition is central to our understanding of its ultimate fate. Current observations indicate that the universe is flat and dominated by dark energy, a force that drives its accelerated expansion. However, the nature of dark energy remains one of the greatest enigmas in physics. Is it a constant, as suggested by Einstein's cosmological constant, or does it evolve over time? Could it be a manifestation of a new, undiscovered field, or perhaps an artifact of our incomplete understanding of gravity on cosmic scales? The CMB's anisotropies offer a stringent test for these hypotheses, constraining the parameters of dark energy's equation of state. Future surveys such as the Euclid mission and the Vera Rubin Observatory's Legacy Survey of Space and Time aim to refine these measurements, potentially revealing whether dark energy is a fixed property of space-time or a dynamic force that changes with time. Such discoveries could redefine our understanding of the universe's destiny, determining whether it will expand forever, collapse in a big crunch, or undergo a more exotic transformation. Equally compelling is the quest to uncover the nature of dark matter, the invisible scaffolding upon which the universe's structure is built. While the CMB provides indirect evidence for dark matter's existence through its gravitational influence on the large-scale distribution of galaxies, the particle or field responsible for this substance remains elusive. Theories abound from weakly interacting massive particles, WMAPs, to axions and sterile neutrinos, each proposing different mechanisms for dark matter's interaction with ordinary matter. Experiments such as the Large Underground Xenon LUT detector and the Axion Dark Matter Experiment, ADMX, seek to detect these hypothetical particles, while the CMB continues to serve as a critical tool for constraining their properties. By analyzing the CMB's acoustic oscillations, the rhythmic patterns of temperature fluctuations, scientists can infer the amount of dark matter present in the early universe, offering clues about its composition and behavior. The interplay between CMB data and particle physics experiments exemplifies the intertism-plary nature of modern cosmology, where insights from one field inform and refine the others. Beyond dark matter and dark energy, the CMB also holds the potential to illuminate the physics of the very early universe, including the enigmatic period of inflation. While the inflationary model successfully addresses the horizon and flatness problems, the specific mechanism driving inflation remains uncertain. Theoretical models such as chaotic inflation, hybrid inflation, and string theory-inspired scenarios each predict distinct features in the CMB's polarization patterns. The detection of primordial gravitational waves, ripples in spacetime generated during inflation, would provide definitive evidence for the inflationary paradigm, confirming its role in shaping the universe's structure. The search for these waves continues with experiments like the South Pole Telescope and the Simons Observatory, which aim to measure the faint B-mode polarization signature in the CMB. Should such a signal be found, it would not only validate inflation, but also provide a glimpse into the energy scale of the early universe, potentially linking cosmology to the realm of high-energy physics and quantum gravity. The CMB also invites us to consider the broader philosophical implications of our cosmic origins. The fact that we can observe this relic of the universe's infancy underscores the interconnectedness of all things. The photons that reach us today have traveled for nearly the entire age of the universe, their journeys shaped by the expansion of space itself. In a sense, we are not passive observers of the cosmos, but active participants in its ongoing story. The elements that compose our bodies, carbon, oxygen, and iron, were forged in the hearts of stars, the remnants of which are scattered across the universe. The CMB in turn is a testament to the conditions that gave rise to these stars, and by extension to life itself. This realization fosters a profound sense of unity between the observer and the observed, reminding us that our existence is deeply entwined with the history of the universe. As we continue to explore the CMB, we must also acknowledge the limitations of our current understanding. The data we collect is subject to interpretation, and the models we develop are approximations of a reality that may transcend our conceptual frameworks. The universe, in all its complexity, may harbor truths that defy our intuition, requiring new paradigms to fully grasp. The pursuit of knowledge is not a linear path, but a spiral, where each discovery opens new avenues of inquiry. The CMB, with its intricate patterns and profound implications, is a testament to the enduring mystery of the cosmos, a reminder that even as we unlock its secrets, the universe will continue to surprise us with its depth and beauty. In the grand narrative of science, the CMB stands as a cornerstone, a relic that bridges the gap between the observable and the theoretical. It is a testament to the power of human curiosity and the resilience of the scientific method. Through the CMB, we have come to understand the universe's age, composition, and structure, yet these achievements are but the first steps in a much longer journey. The questions raised by the CMB about the nature of dark matter, the origin of the universe, and the fate of all things will continue to drive the next generation of discoveries. As we refine our instruments and expand our horizons, we move ever closer to answering the fundamental question that has inspired humanity for millennia: what is the nature of the universe, and what place do we occupy within it? In the end, the CMB is more than a scientific phenomenon. It is a symbol of our collective quest for knowledge, a reminder that the universe is both comprehensible and infinitely complex. It challenges us to reconcile the quantum realm with the macroscopic world, to grapple with the paradoxes of time and space, and to imagine what may lie beyond the veil of the observable. In the CMB, we find not just the echoes of the past, but the questions that will propel us into the future. As we continue our exploration, let us carry with us the humility of knowing that the universe is vast, its secrets countless, and in that humility let us find inspiration to dream, to discover, and to seek the truths that lie hidden in the faint glow of the cosmic microwave background. The Big Bang is often mischaracterized as an explosion within the confines of space, a fiery spectacle that hurled matter outward. However, the truth is far more profound. The Big Bang was not an explosion in space, but rather an expansion of space itself. This distinction is crucial because it reshapes our understanding of the universe's origin. Imagine a cosmic canvas being stretched and pulled, where every point in the fabric of reality is moving away from every other. This expansion birthed the universe as we know it, setting the stage for the intricate dance of matter, energy, and time. At the heart of this cosmic narrative lies the cosmic microwave background, CMB, a remnant of this primordial event, often referred to as the afterglow of the Big Bang. The CMB is a faint, pervasive radiation that fills the universe today. It is a relic from the very early moments of the cosmos, approximately 380,000 years after the Big Bang, when the universe had cooled sufficiently for electrons to combine with nuclei to form neutral atoms. This pivotal moment, known as recombination, allowed photons to travel unimpeded through the now transparent universe, marking the end of the so-called Dark Ages. The CMB serves as a direct and irrefutable evidence of the universe's explosive beginning. Its uniformity across the sky and the slight temperature fluctuations it exhibits are like the fingerprints left behind by the universe's earliest moments. These minute variations, which are only one part in 100,000, reveal the seeds of future cosmic structures, galaxies and clusters of galaxies that would eventually emerge from the dense, hot soup of the early universe. As scientists peer into the depths of the cosmos, they find themselves gazing back in time, observing the universe in its infancy. The CMB provides a window into this ancient past, allowing researchers to study the conditions that prevailed just moments after the Big Bang. It is a celestial whisper that echoes through the void, a testament to the incredible journey of the universe from a singular point of infinite density to the vast expanse we inhabit today. The study of the CMB not only confirms the Big Bang theory, but also deepens our appreciation for the interconnectedness of all things in the cosmos, inviting us to ponder our place in this grand narrative of creation and expansion. The universe's journey began in a state of unimaginable heat and density, a singularity where the laws of physics, as we know them, ceased to function. In the first fraction of a second, specifically during the Planck epoch, the universe was a seething cauldron of energy, governed by quantum fluctuations and the four fundamental forces unified in a single framework. However, as time elapsed, the universe expanded exponentially, a process known as cosmic inflation, which lasted for a mere 10^36 seconds. During this brief yet transformative period, quantum fluctuations, tiny ripples in the fabric of space-time, were stretched across vast distances, sowing the seeds for the large-scale structure of the cosmos. As inflation came to an end, the universe transitioned into a new phase marked by a rapid cooling. This cooling allowed the fundamental forces to separate, leading to the formation of particles, such as quarks and gluons, which would later coalesce into protons and neutrons. Within the first few minutes of the universe's existence, a process known as nucleosynthesis began, where these particles combined to form the light elements, hydrogen and helium. This was a critical moment in the universe's development, as the abundance of these elements laid the groundwork for the formation of stars and galaxies in the eons to come. The universe continued to cool and expand, and as it did, the density of matter decreased. Approximately 380,000 years after the Big Bang, the universe reached a temperature where electrons could finally combine with nuclei to form neutral atoms. This epoch, known as recombination, marked a significant turning point in the universe's history. With the formation of neutral atoms, photons, particles of light, could now travel freely through space without being scattered by free electrons. This momentous event is what ultimately gave rise to the cosmic microwave background, CMB, the ancient light that permeates the universe today. The CMB is not merely a remnant of the universe's early days. It is a treasure trove of information about the conditions that existed during recombination. As the universe expanded, the wavelengths of these photons stretched, shifting from visible light to microwave radiation. Today, the CMB is observed as a nearly uniform glow filling the universe. With a temperature of approximately 2.7 Kelvin, this uniformity is a testament to the universe's homogeneity at that time, while the subtle temperature variations, or anisotropies, provide clues about the density fluctuations that would lead to the formation of cosmic structures. These fluctuations, though minute, are essential for understanding the distribution of matter in the universe today. They represent the gravitational seeds from which galaxies, stars, and planets would eventually arise. The CMB thus serves as a cosmic map, revealing the intricate web of structure that defines our universe. By studying these fluctuations, scientists can infer the properties of the early universe, including the amounts of dark matter and dark energy that play vital roles in the cosmos evolution. As we reflect on the universe's journey from the singularity of the Big Bang to the emergence of the CMB, we are reminded of the delicate balance of forces that govern our existence. The universe's expansion, the formation of matter, and the intricate dance of particles and energy all contribute to the rich tapestry of the cosmos. The CMB stands as a silent witness to these events, a reminder of the universe's humble beginnings and the awe-inspiring processes that have shaped its current form. In this way, the study of the CMB not only illuminates the past, but also invites us to contemplate our place in the vast, ever-expanding universe. The cosmic microwave background, CMB, is not just a relic of the universe's infancy. It is a cornerstone of modern cosmology, providing profound insights into the nature of our universe. One of the most compelling pieces of evidence supporting the Big Bang theory is the CMB's near-perfect black body spectrum. A black body is an idealized object that absorbs all incident electromagnetic radiation and emits radiation with a spectrum determined solely by its temperature. The fact that the CMB so closely matches this theoretical spectrum is a remarkable confirmation of the universe's thermal history. This perfect alignment suggests that the CMB originated from a hot, dense state, reinforcing the notion that the universe began in a fiery explosion. Moreover, the CMB's uniformity across the sky, with only slight temperature variations, presents a fascinating challenge to our understanding of the early universe. While these tiny fluctuations may seem insignificant at first glance, they are actually the seeds of all structure in the cosmos. These temperature differences correspond to density variations in the primordial plasma, which would eventually lead to the formation of galaxies and galaxy clusters. The CMB thus acts as a cosmic map, illustrating the initial conditions that set the stage for the universe's evolution. The study of these anisotropies has allowed scientists to measure the universe's geometry and composition, revealing the presence of dark matter and dark energy, which together account for the majority of the universe's mass-energy content. However, the CMB also raises intriguing questions that challenge our current understanding of cosmology. One of the most perplexing issues is the so-called horizon problem, which questions why the CMB appears so uniform in temperature across regions of the universe that have never been in causal contact. In other words, certain parts of the universe are so far apart that even light, the fastest thing in the universe, hasn't had enough time to travel between them since the Big Bang. Despite this lack of communication, these distant regions exhibit nearly identical temperatures. This uniformity is difficult to reconcile with the standard Big Bang model, which posits that different regions of the universe could not have influenced each other due to the finite speed of light. To address this conundrum, scientists have proposed the theory of cosmic inflation. Inflation suggests that the universe underwent a period of exponential expansion in the first fractions of a second after the Big Bang, during which regions that were initially close enough to interact were rapidly stretched apart. This rapid expansion would have smoothed out any irregularities in temperature and density, resulting in the uniform CMB we observe today. Inflation not only solves the horizon problem, but also explains other features of the universe, such as its flatness and the absence of magnetic monopoles. Yet, even with the introduction of inflation, there remain unanswered questions about the nature of the early universe and the mechanisms that drive its expansion. What triggered inflation and what caused it to end? These inquiries lie at the heart of ongoing research in cosmology, as scientists strive to understand the fundamental forces that govern the universe. The CMB continues to be a focal point for these investigations, offering a unique opportunity to probe the conditions that existed just moments after the Big Bang. In essence, the CMB serves as a cosmic tapestry woven with the threads of time, space, and matter. Its study allows us to glimpse the universe's origins and to unravel the mysteries of its evolution. As we delve deeper into the data provided by the CMB, we are not only piecing together the history of the cosmos, but also confronting the limits of our knowledge. The quest to understand the CMB is a testament to humanity's insatiable curiosity and our desire to comprehend the vast, intricate universe that surrounds us. In the face of the unknown, the CMB remains a guiding light, illuminating the path toward a greater understanding of our place in the cosmos. As we grapple with the implications of the CMB and the horizon problem, we are led to a radical yet elegant hypothesis. The universe once expanded at speeds surpassing the speed of light itself. This notion, known as cosmic inflation, challenges our conventional understanding of physics and opens the door to a deeper exploration of the universe's earliest moments. Inflationary theory proposes that the universe experienced a period of exponential growth in the first fractions of a second after the Big Bang, during which the fabric of space stretched at an extraordinary rate. This rapid expansion would have effectively erased any pre-existing irregularities, smoothing out the temperature variations that we observe in the CMB today. The concept of inflation not only addresses the horizon problem, but also offers explanations for other cosmic enigmas, such as the universe's flatness and the uniform distribution of matter. By envisioning a universe that could expand faster than the speed of light, we confront the limitations of our classical understanding of space and time. Such a perspective invites us to consider that the very laws governing the universe might have operated differently in its infancy, governed by principles we have yet to fully comprehend. This transition from the familiar to the extraordinary compels us to rethink our assumptions about the cosmos. As we delve into the theory of cosmic inflation, we are not merely exploring a scientific hypothesis. We are embarking on a journey into the heart of the universe's most profound mysteries. The implications of this theory stretch far beyond the horizon problem, prompting us to ponder the nature of reality itself and our place within it. With the foundation laid by the CMB and the insights it provides, the stage is set for a deeper investigation into the mechanisms that propelled the universe into its current state. What forces initiated inflation, and what caused it to halt? These questions beckon us forward, urging us to pursue the answers that lie hidden in the fabric of space-time. The quest to understand the universe is an ongoing adventure, one that transcends the boundaries of science and philosophy, inviting us to explore the very essence of existence. In the next segment, we will dive into the theory of cosmic inflation, unraveling the complexities that define our universe's extraordinary journey from chaos to order. Imagine standing at the edge of the observable universe, gazing outward into the vast expanse of space. Beyond the familiar constellations and distant galaxies, the universe stretches in every direction, its boundaries defined by the cosmic microwave background, CMB, a relic of the earliest moments after the Big Bang. This faint glow, a remnant of the universe's infancy, is nearly uniform in temperature, varying by less than 1/10,000th of a degree across the sky. Yet this apparent harmony poses a profound puzzle. How could opposite sides of the universe, separated by billions of light years, share the same temperature if they have never been in contact? After all, the speed of light sets the ultimate limit on how quickly information can travel, and the universe is simply too young for signals to have traversed such distances since the Big Bang. This contradiction, known as the horizon problem, challenges the very foundation of our understanding of cosmic history. If the universe had always expanded at a steady rate, as the standard Big Bang model suggests, distant regions would have remained forever out of reach, unable to exchange energy or influence one another. And yet the CMB reveals a startling homogeneity, an almost perfect equilibrium in temperature that defies explanation unless some mechanism allowed these distant parts to communicate long ago. This mystery has led scientists to propose a radical solution: cosmic inflation. In this fleeting instant, a mere fraction of a second after the Big Bang, the universe underwent an extraordinary transformation. Space itself expanded at an unimaginable pace, growing exponentially in size, far beyond the limits imposed by the speed of light. This period of accelerated expansion, though brief, reshaped the cosmos in ways that still echo through time. It smoothed out the irregularities in density and temperature, setting the stage for the CMB's uniformity. More than just a solution to the horizon problem, inflation offers a glimpse into the universe's most enigmatic origins, a moment when the fabric of reality stretched beyond comprehension, driven by forces we are only beginning to understand. As we peer deeper into the cosmos, the echoes of this primordial event remain etched into the very structure of the universe, waiting to be deciphered by those who dare to explore the unknown. At the heart of cosmic inflation lies a concept that defies intuition. The universe expanded faster than the speed of light. This seemingly impossible feat is not a violation of Einstein's theory of relativity, but rather a consequence of the unique nature of space itself. According to general relativity, while no object can move through space faster than light, space itself can expand at any rate. During inflation, this expansion was not merely rapid, it was exponential, meaning that the universe doubled in size at regular intervals in an incredibly short span of time. approximately 10^32 seconds, the universe grew by a staggering factor of 10^26. To grasp the magnitude of this growth, consider that if you were to stretch a single proton to the size of the observable universe today, the universe during inflation would have expanded from a subatomic scale to a size roughly equivalent to a grapefruit in an instant. This explosive expansion compressed the universe into a nearly perfect sphere of uniform density and temperature, resolving the horizon problem by ensuring that all regions of space had once been in causal contact before being rapidly separated. The driving force behind this hyper-accelerated expansion is believed to be a hypothetical energy field known as the inflaton field. Unlike ordinary matter or energy, the inflaton field possessed a peculiar property. It exerted negative pressure, causing space to expand at an accelerating rate. This behavior is analogous to the repulsive force observed in dark energy, which is currently driving the universe's accelerated expansion today. However, unlike dark energy, the inflaton field did not persist indefinitely. Instead, it decayed rapidly, releasing an immense amount of energy in a process known as reheating. This sudden release of energy marked the end of inflation and initiated the hot, dense phase of the universe, described by the standard Big Bang model. From this point forward, the universe continued to expand, but at a much slower and more familiar pace, allowing the first particles and radiation to form. One of the most fascinating aspects of inflation is its ability to explain the origin of large-scale structure in the universe. While the inflaton field smoothed out the universe's overall density, it did not erase all fluctuations. Instead, quantum fluctuations, tiny ripples in the fabric of space-time, were imprinted onto the inflating universe. These microscopic perturbations, amplified by the exponential expansion, became the seeds for the formation of galaxies and galaxy clusters. As the universe cooled and matter condensed under the influence of gravity, these initial density variations gave rise to the cosmic web we observe today. The cosmic microwave background provides a direct imprint of these early fluctuations, revealing a subtle pattern of temperature variations that correspond precisely to the predictions of inflationary theory. This remarkable agreement between observation and theory underscores the power of inflation as a framework for understanding the universe's earliest moments. Cosmic inflation not only resolves the horizon and flatness problems, but also opens the door to profound questions about the nature of our universe and its place in a potentially vaster multiverse. One of the most intriguing implications of inflation is its role in addressing the flatness problem. The observation that the universe appears to be geometrically flat, with a curvature so close to zero that it defies simple explanation. In the absence of inflation, the universe's density would have needed to be fine-tuned to an extraordinary degree to produce the observed flatness, a scenario akin to balancing a pencil perfectly on its tip. Inflation elegantly circumvents this issue by driving the universe toward flatness during its exponential expansion. The rapid stretching of space effectively diluted any initial curvature, leaving behind a universe that appears remarkably flat on large scales. This outcome aligns closely with observations from the Planck satellite, which measured the CMB with unprecedented precision and confirmed the near-flat geometry of the cosmos. Yet, for all its explanatory power, inflation raises new questions that challenge our understanding of the universe's origins. Chief among these is the question of what triggered inflation in the first place. The inflation field, while theoretically compelling, remains a hypothetical construct, and its properties are not yet fully understood. Scientists speculate that inflation may have been initiated by quantum fluctuations in the early universe, or by some unknown interaction between fundamental forces. However, these hypotheses remain speculative, and the precise mechanism that activated the inflation field and then caused it to decay remains elusive. Moreover, the energy scale at which inflation operated is extraordinarily high, approaching conditions that are inaccessible to even the most advanced particle accelerators. This gap in our knowledge highlights the limitations of current physics and underscores the need for a unified theory that can reconcile quantum mechanics with general relativity. Perhaps the most mind-bending implication of inflation is the possibility of a multiverse, a vast ensemble of universes, each with its own distinct properties, born from the same inflating space-time. Inflation does not necessarily end everywhere at once. Instead, it can continue indefinitely in certain regions of space, giving rise to a phenomenon known as eternal inflation. In this scenario, the inflaton field decays in some regions, forming pocket universes like ours, while remaining active in others, perpetuating the cycle of exponential expansion. This theoretical framework suggests that our universe is but one bubble in an infinite sea of expanding domains, each governed by different physical laws and constants. While this idea remains highly speculative, it offers a tantalizing possibility that the universe we inhabit is not unique, but one of countless possibilities existing simultaneously in a higher dimensional landscape. The search for evidence of eternal inflation and the multiverse hinges on the study of the CMB's polarization patterns. Specifically, scientists are looking for subtle distortions in the CMB's polarization, known as B-mode polarization, which could serve as a signature of gravitational waves generated during inflation. These ripples in spacetime, produced by the violent expansion of the early universe, would leave an indelible mark on the CMB, detectable only through highly sensitive instruments. The BICEP 2 experiment in Antarctica initially claimed to have detected B-mode polarization in 2014, but subsequent analysis revealed that the signal was likely due to interstellar dust rather than primordial gravitational waves. Since then, researchers have refined their techniques, using observatories such as the Atacama Cosmology Telescope and the South Pole Telescope to minimize foreground contamination. The upcoming LightBird satellite mission, scheduled for launch in the 2030s, aims to provide the most comprehensive search for B-mode polarization to date, potentially offering the first observational confirmation of inflation and its connection to the multiverse. Beyond the search for gravitational waves, inflation also invites us to reconsider the philosophical implications of our existence. If our universe is but one of many, what does that mean for the uniqueness of life and the laws of physics that govern it? Could there be other universes where the constants of nature differ slightly, rendering the formation of stars, planets, or even life impossible? Or perhaps, in some distant pocket of the multiverse, conditions are just right for entirely different forms of complexity and consciousness to emerge. These questions, while speculative, challenge our perception of reality and invite us to imagine a cosmos far grander and more intricate than we can yet comprehend. Inflation's implications extend beyond the realm of cosmology, influencing fields as diverse as particle physics, mathematics, and even philosophy. Theorists continue to explore alternative models of inflation, such as hybrid inflation and chaotic inflation, each proposing different mechanisms for initiating and ending the inflating phase. Meanwhile, mathematicians grapple with the implications of eternal inflation for probability and the measure problem, which seeks to determine the likelihood of different universes arising in a multiverse. Philosophers, too, are drawn to the questions raised by inflation, pondering the nature of existence and whether the laws of physics are truly universal. As we stand on the precipice of these discoveries, the legacy of inflation continues to shape our understanding of the cosmos. It reminds us that the universe is not a static entity, but a dynamic and evolving system, capable of birthing entire realities in the blink of an eye. The quest to uncover the secrets of inflation is not merely an exercise in scientific curiosity. It is a journey to understand our place in the grand tapestry of existence, where the past, present, and future are woven together by the invisible threads of spacetime. While cosmic inflation offers a compelling resolution to the universe's uniformity and flatness, it does not tell the full story of how the cosmos evolved into the intricate web of galaxies and superclusters we see today. The final piece of this cosmic puzzle lies in the subtle variations embedded in the cosmic microwave background, CMB, the universe's oldest light. These minute temperature fluctuations, though imperceptible to the naked eye, contain the genetic code of the universe's large-scale structure. They are the echoes of quantum fluctuations magnified by inflation, transformed into density variations that would eventually give rise to the vast cosmic architecture of stars, galaxies, and galaxy clusters. By studying the CMB in exquisite detail, scientists can trace the evolution of these primordial ripples, mapping the birth pangs of the universe and unraveling the processes that shaped its destiny. The CMB's temperature map, captured by satellites such as the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck spacecraft reveals a stunningly intricate pattern of hot and cold spots. These variations, though infinitesimal on the order of 0.000002 degrees Celsius, carry profound significance. They represent the earliest imprints of density fluctuations in the universe, moments when the fabric of space-time was still a seething cauldron of quantum uncertainty. In the aftermath of inflation, these fluctuations were frozen into the fabric of the universe, becoming the seeds for future structure. As the universe expanded and cooled, regions with slightly higher densities began to attract surrounding matter through gravity, forming the first clumps of gas that would eventually collapse into stars and galaxies. This process, known as gravitational instability, set the stage for the universe's transformation from a featureless expanse to a vibrant tapestry of celestial wonders. Yet the journey from the CMB's temperature map to the formation of galaxies is far from straightforward. The initial density fluctuations were far too small to account for the vast structures we observe today. To bridge this gap, dark matter plays a crucial role. Unlike ordinary matter, which interacts with electromagnetic radiation, dark matter neither emits nor absorbs light, making it invisible to telescopes. However, its gravitational pull is undeniable. In the early universe, dark matter provided the scaffolding upon which ordinary matter could coalesce, amplifying the effects of the CMB's density variations. Without dark matter's unseen hand, the universe might have remained a diffuse cloud of gas, devoid of the rich diversity of cosmic structures we now admire. The interplay between dark matter and ordinary matter, guided by the gravitational forces imprinted in the CMB, ultimately determined the distribution of galaxies and the intricate networks of filaments and voids that define the cosmos. As we turn our gaze to the CMB's temperature map, we are not merely observing the universe's infancy, we are peering into the blueprint of its future. Each fluctuation is a whisper from the past, a message carried through eons, waiting to be deciphered. The next step in this cosmic narrative requires delving deeper into these temperature variations, tracing their evolution through time, and uncovering the hidden forces that shaped the universe's grand design. The story of galaxy formation begins not in the present day, but in the ancient light of the CMB, where the seeds of all that is visible were sown. In the vast silent expanse of the cosmos, a whisper from the dawn of time persists, a faint glow that bathes the universe in a soft ethereal light, known as the cosmic microwave background, CMB. This radiation is the oldest light we can observe, a relic from an era just 380,000 years after the Big Bang. Yet despite its age and ubiquity, the CMB is far from uniform. It carries a subtle, almost imperceptible texture, a delicate mosaic of hot and cold spots, each no larger than a degree across the sky. These fluctuations, smaller than the flicker of a candle seen from a mile away, are not mere accidents of nature. They are the fingerprints of the universe's infancy etched into the fabric of space itself. To the untrained eye, they might resemble static, a cosmic snowstorm. But to astrophysicists, they are a treasure trove of information, a cosmic barcode encoding the fundamental properties of existence. Every wrinkle, every shadow in this ancient map tells a story of the universe's birth, its evolution, and its ultimate fate. Imagine holding a single page from the universe's earliest diary. The CMB is precisely that, a fossilized snapshot of the primordial soup frozen in time. Its patterns reveal the seeds of galaxies, the balance of matter and energy, and the forces that shaped the cosmos. Yet even as we marvel at this celestial artifact, we are confronted with a humbling truth. The universe is mostly invisible to us. Only a fraction of its contents are made of the familiar atoms that constitute stars, planets, and life itself. The rest is composed of enigmatic substances, dark matter and dark energy, that defy direct observation. The CMB, however, offers a rare window into these hidden realms, allowing us to peer beyond the veil of ignorance and glimpse the architecture of reality. To understand the significance of the CMB's temperature map, we must first grasp the scale of its achievement. This map is not merely a scientific curiosity. It is a Rosetta Stone for cosmology, a key to deciphering the universe's deepest secrets. The tiny temperature variations, measured in millionths of a degree, hold the answers to questions that have haunted humanity for millennia. What is the universe made of? How did it begin? And where is it heading? As we embark on this exploration, let us consider the CMB not just as a scientific tool, but as a bridge connecting our fleeting existence to the infinite. In its faint glow, we find a mirror reflecting the grandeur and mystery of the cosmos. To unravel the secrets embedded in the CMB's temperature map, scientists have deployed some of the most sophisticated instruments ever conceived. Among them, the European Space Agency's Planck satellite stands as a testament to human ingenuity. Launched in 2009, Planck spent over 4 years mapping the CMB with unprecedented precision, capturing temperature differences as minor as 0.0001 degrees Celsius. To put this into perspective, such a variation is akin to detecting the heat of a single cup of tea buried deep within the ice of Antarctica. These infinitesimal fluctuations, though imperceptible to the naked eye, are the echoes of quantum fluctuations magnified by the rapid expansion of the early universe. They represent the first ripples in space-time, the precursors to the cosmic web of galaxies and voids that now dominate the heavens. The anisotropies in the CMB, the slight variations in temperature, are not random. They arise from density fluctuations in the primordial plasma that filled the universe. Before the CMB was emitted, in the early cosmos, regions with slightly higher densities were hotter, as gravity pulled matter together, increasing pressure and temperature. Conversely, less dense areas were cooler. Over time, these density variations acted as gravitational seeds, influencing the formation of galaxies and galaxy clusters. However, the process was not instantaneous. Before the universe became transparent, photons were trapped in a dense fog of electrons and protons, colliding constantly with charged particles. This created a kind of cosmic resonance, where sound waves, acoustic oscillations, rippled through the plasma. These oscillations left imprints on the CMB, creating a pattern of peaks and troughs in the temperature map. By studying the angular scale of these peaks, scientists can deduce the geometry of the universe, the density of its constituents, and even the rate at which it is expanding. The power of the CMB map lies in its ability to serve as a cosmic laboratory. For instance, the relative heights and widths of the acoustic peaks provide critical insights into the proportions of ordinary matter, dark matter, and dark energy. Ordinary matter, the stuff of stars, planets, and people, interacts strongly with electromagnetic forces, making it visible and measurable. Dark matter, on the other hand, exerts gravitational influence, but does not emit or absorb light, remaining elusive. Its presence is inferred from the way galaxies rotate and cluster. Dark energy, even more mysterious, is a hypothetical form of energy that permeates space and drives its accelerated expansion. Together, these three components shape the universe's destiny, yet their exact nature remains shrouded in uncertainty. The CMB map acts as a cosmic ledger, quantifying their contributions with astonishing precision. One of the most striking revelations from Planck's observations is the composition of the universe. Approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. This distribution, known as the lambda-cold dark matter (LACE) model, has become the standard framework for modern cosmology. The dominance of dark matter and dark energy underscores the limitations of human perception. If we were to imagine the universe as a vast ocean, we would be adrift on the surface, oblivious to the immense depths below. Yet the CMB allows us to dive beneath the waves, probing the unseen currents that govern the cosmos. Through meticulous analysis of its temperature map, scientists have reconstructed the universe's evolutionary timeline, tracing its journey from a searing singularity to the sprawling, intricate structure we observe today. The CMB's power extends beyond its immediate implications. It also provides constraints on fundamental physics, testing theories ranging from inflation, the rapid exponential expansion of the early universe, to the nature of neutrinos. For example, the timing and amplitude of the acoustic peaks offer evidence for inflation, which explains why the universe appears so homogeneous and flat on large scales. Moreover, the CMB's polarization patterns, detected by missions like the Wilkinson Microwave Anisotropy Probe and Planck, reveal the imprint of gravitational waves generated during inflation. These findings not only validate theoretical models, but also open new avenues for exploring the quantum origins of the cosmos. In essence, the CMB temperature map is a multi-dimensional puzzle, each piece contributing to a grander picture. Its resolution requires not just technological prowess, but also a deep understanding of the interplay between gravity, thermodynamics, and quantum mechanics. By decoding this map, scientists have transformed our perception of the universe, revealing a cosmos far stranger and more complex than previously imagined. Yet, for all its revelations, the CMB also reminds us of the vastness of our ignorance. The very act of measurement brings clarity, but it also highlights the frontiers of the unknown, beckoning us to probe deeper into the fabric of reality. The CMB's temperature map is a triumph of science, yet it also lays bare the limits of human knowledge. While it provides precise measurements of the universe's composition, it does not answer the most profound question: what are dark matter and dark energy? These entities, which constitute over 95% of the universe's total mass energy content, remain spectral presences, their true nature concealed behind layers of mystery. Their existence is inferred solely through their gravitational effects. Dark matter by the way galaxies clump together, and dark energy by the accelerating expansion of the cosmos. But what if these phenomena are not substances at all, but manifestations of our incomplete understanding of gravity itself? Could Einstein's theory of general relativity, which describes gravity as the curvature of space-time, require modification on cosmic scales? Such possibilities challenge the foundations of modern physics, forcing scientists to confront the uncomfortable reality that our current models may be missing crucial pieces of the puzzle. Dark matter, in particular, presents a paradox. It interacts gravitationally, forming halos around galaxies, acting as the scaffolding upon which visible matter coalesces. Yet it does not emit, absorb, or reflect electromagnetic radiation, rendering it invisible to telescopes. The leading hypothesis posits that dark matter consists of weakly interacting massive particles, WMAPs, hypothetical particles that rarely interact with ordinary matter, except through gravity and the weak nuclear force. Experiments like the Large Hadron Collider and underground detectors such as XN1T have sought to capture these elusive particles, but so far, none have been conclusively identified. Another contender is AXN's lightweight particles proposed to resolve issues in quantum chromodynamics. Despite decades of research, the identity of dark matter remains one of the greatest unsolved problems in astrophysics. If dark matter is a substance, dark energy is even more enigmatic. Unlike dark matter, which clumps and aggregates under gravity, dark energy behaves like a repulsive force, driving galaxies apart at an accelerating rate. Its existence was confirmed in the late 1990s through observations of distant supernovae, but its origin remains a mystery. Is it a property of space itself, a cosmological constant, as Einstein once speculated, or could it be a dynamic field, such as quintessence, whose strength varies over time and space? The CMB offers tantalizing clues. For instance, the precise fit of the LNCDM model to Planck data suggests that dark energy is indeed a cosmological constant. But this conclusion hinges on the assumption that general relativity holds true on the largest scales. Alternative theories such as modified gravity models propose that the observed acceleration is not due to dark energy, but rather an artifact of how gravity behaves in the vast emptiness of intergalactic space. These debates highlight the delicate interplay between observation, theory, and interpretation in cosmology. Beyond the scientific challenges, the dominance of dark matter and dark energy raises existential questions. If the universe is predominantly composed of substances we cannot see or touch, what does this imply about our place in the cosmos? Are we merely observers of a reality that defies our intuition? Or is there a deeper principle at work, one that we have yet to uncover? The CMB map, with its precise quantification of the unseen, serves as both a beacon and a reminder. It illuminates the vastness of the unknown, while underscoring the fragility of human understanding. In this light, the pursuit of knowledge becomes not just a scientific endeavor, but a philosophical journey, a quest to reconcile the observable with the unfathomable. Moreover, the CMB's revelations challenge our anthropocentric worldview. For centuries, humans have assumed that the universe is comprehensible, that its laws are uniform and discoverable. Yet the dominance of dark matter and dark energy suggests that the cosmos may be governed by principles far removed from our everyday experience. Imagine a universe where the majority of its substance exists in forms beyond the reach of our senses, where the very fabric of reality is shaped by forces we have only begun to grasp. In such a cosmos, the notion of mastery over nature becomes untenable. Instead, we are invited to adopt a posture of humility, recognizing that our understanding is provisional, and that the universe's grand design may forever elude complete comprehension. The CMB map, therefore, is more than a scientific document. It is a testament to the interplay between discovery and mystery. It shows us the universe as it was, yet leaves unanswered the questions of its essence. It reveals the structure of the cosmos, yet obscures the mechanisms that sustain it. In this duality lies the beauty of the scientific enterprise, a perpetual dance between the known and the unknown, where each answer births new questions. As we stand at the edge of this vast frontier, we are reminded that the universe is not a puzzle to be solved, but a story to be explored, one chapter at a time. To fully appreciate the CMB's role as a cosmic barcode, we must trace its origins to the moment when the universe transitioned from opacity to transparency, a pivotal event that set the stage for the light we now observe. In the earliest moments of the Big Bang, the universe was a seething plasma of subatomic particles too hot and dense for atoms to form. Photons, the carriers of light, were constantly scattered by free electrons, unable to travel freely through space. This cosmic fog persisted for hundreds of thousands of years, until the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. This process, known as recombination, marked the end of the Dark Ages and the beginning of the universe's transparency. With electrons bound into atoms, photons were finally free to traverse the cosmos, setting off on an unbroken journey that would last billions of years. The light released during this epoch of recombination is the CMB we detect today. Though stretched by the expansion of the universe, it retains the imprints of the early cosmos, offering a snapshot of the universe at a time when it was a mere infant. To understand the CMB in its full context, we must return to this moment of transformation, where the universe shed its primordial darkness and allowed light to take its first steps across the void. In doing so, we move beyond the static map of temperature fluctuations and into the dynamic narrative of the universe's birth. The CMB is not just a relic of the past, it is a messenger from the dawn of time, carrying with it the echoes of forces and events that continue to shape the cosmos. As we follow the path of this ancient light, we prepare to uncover the story of how the universe came to be and how it will unfold in the eons to come. In the moments following the Big Bang, the universe was an inferno of energy, a searing expanse where matter and radiation were locked in a relentless dance. Photons, the fundamental carriers of light, collided endlessly with free electrons and protons, scattering in all directions. This constant interaction prevented light from traveling freely, rendering the cosmos an opaque, incandescent sea. The universe, though teeming with energy, was a place of darkness, not the absence of light, but rather a realm where light could not propagate unimpeded. This period, known as the photon-baryon plasma phase, lasted for hundreds of thousands of years, a time when the universe was still too hot for stable atoms to form. As the universe expanded, it gradually cooled, and the once unified forces began to take their distinct forms. The temperature, initially measured in billions of degrees, steadily declined, allowing the dense plasma to evolve. Electrons and protons, previously too energetic to combine, began to slow down. This marked the beginning of a crucial transformation, the moment when the universe would transition from a chaotic, luminous fog to a transparent expanse where light could finally travel unobstructed. Yet for 380,000 years, the cosmos remained cloaked in this dense, glowing veil, an unseen era where no eye could witness the unfolding drama. The lack of direct observation from this epoch presents one of the greatest mysteries of astrophysics. Before recombination, the universe was a vast, invisible ocean of plasma where photons were trapped in a ceaseless cycle of absorption and emission. There were no stars, no galaxies, only the raw ingredients of future cosmic structures. The universe was in a state of equilibrium, with radiation and matter locked in a delicate balance. Any attempt to peer into this primordial darkness is met with a wall of impenetrable heat and density, a barrier that obscures the earliest moments of existence. Yet, even in this darkness, the universe was preparing for a momentous shift. The conditions were slowly changing, the temperature dropping, the particles moving with less vigor. The stage was being set for a cosmic event that would redefine the nature of the cosmos. As the universe continued to cool, the time was approaching when electrons and protons would finally unite, forming neutral hydrogen and allowing light to escape. This moment, known as recombination, would mark the end of the cosmic fog and the birth of the observable universe. It was a turning point in cosmic history, a moment when the universe transformed from a place of chaos into one where light could begin its long journey across the cosmos. As the universe continued to expand, the relentless passage of time brought about a subtle yet profound change in its composition. The initial fireball that had filled the cosmos with searing radiation gradually lost intensity as space itself stretched outward. With each passing moment, the average kinetic energy of particles diminished, and the once unified plasma began to evolve. The temperature, initially measured in billions of degrees, steadily declined until it reached a critical threshold, approximately 3000 Kelvin. At this point, the energetic electrons and protons that had remained in a state of constant collision began to slow down enough to allow for a new kind of stability. For the first time since the universe's inception, the conditions were right for electrons to combine with protons, forming neutral hydrogen atoms. This process, known as recombination, marked the end of the photon-baryon plasma phase and the dawn of a new era in cosmic history. Before recombination, the universe was in a state of thermal equilibrium, where radiation and matter were in constant interaction. The photons, unable to travel far before encountering a charged particle, were effectively trapped in a cycle of absorption and re-emission. This radiative trapping ensured that the universe remained opaque, with no possibility for light to escape and propagate across vast distances. However, as the universe cooled and neutral atoms began to form, this delicate balance was disrupted. With fewer free electrons available to scatter photons, the cosmic medium became increasingly transparent. The photons, no longer bound by the ceaseless collisions with charged particles, were finally able to travel unimpeded through space. This momentous shift signaled the end of the cosmic fog and the beginning of a universe where light could reach across the vastness of space. The release of this long-trapped light marked the birth of the cosmic microwave background, CMB, the oldest light in the universe. As the photons decoupled from matter, they were free to move through the expanding cosmos, carrying with them a snapshot of the universe as it appeared just moments after recombination. Though this light was once visible, the subsequent expansion of the universe caused it to undergo a dramatic transformation. Over billions of years, the stretching of space stretched the wavelengths of these photons, shifting them from the visible spectrum into the microwave range. Today, the CMB permeates the entire cosmos, a faint glow that serves as a relic of the universe's infancy. The significance of recombination extends beyond the mere release of light. It represents a fundamental transformation in the structure and evolution of the universe. Before recombination, the universe was governed by the interactions between radiation and matter, with density fluctuations in the plasma giving rise to acoustic oscillations, ripples in the cosmic ocean. These oscillations, imprinted on the CMB, provide invaluable insights into the early universe's composition and behavior. After recombination, the influence of radiation diminished, and gravity took center stage. The formation of neutral hydrogen allowed for the gradual accumulation of matter into denser regions, setting the stage for the formation of the first stars and galaxies. Recombination thus stands as a defining moment in cosmic history, a transition that reshaped the universe's physical properties and opened the door to the observable cosmos. The release of the CMB not only marked the end of the universe's opaque infancy, but also laid the foundation for the structures we see today. It is a testament to the universe's ability to evolve, to transform from a chaotic, blinding expanse into a realm where light could finally illuminate the vastness of space. The cosmic microwave background, CMB, is more than just a relic of the universe's infancy. It is a cosmic map, a window into the earliest moments of existence. Every fluctuation in the CMB's temperature and polarization carries a story, revealing the seeds of structure that would eventually grow into galaxies, stars, and planets. These tiny variations, imprinted on the CMB when the universe was just 380,000 years old, are the echoes of quantum fluctuations in the early universe. These fluctuations, amplified by inflation, a rapid exponential expansion in the first fraction of a second after the Big Bang, became the blueprint for the distribution of matter in the cosmos. By studying the CMB, scientists can trace the origins of the universe's large-scale structure, mapping out the cosmic web that spans billions of light years. However, the CMB is also a boundary, a veil that separates the observable universe from the mysterious era that preceded it. Before recombination, the universe was a dense, opaque plasma where photons were constantly scattered by free electrons. This means that our understanding of the universe's history is limited to the moments after recombination. The CMB, therefore, represents the furthest back we can see into the past using electromagnetic radiation. The epoch that came before, when the universe was a churning cauldron of energy and particles, remains hidden from direct observation. This period, often referred to as the Cosmic Dark Ages, is a time of profound mystery. During these 380,000 years, the universe was devoid of light as we know it, a vast, dark expanse where the only illumination came from the residual heat of the Big Bang itself. The Cosmic Dark Ages are perhaps the most enigmatic chapter in the universe's history. After recombination, the universe entered a phase where it was dominated by neutral hydrogen, with no stars or galaxies to emit light. This period lasted for hundreds of millions of years, ending only when the first stars ignited in distant corners of space. Until then, the universe was a silent, featureless void, a time when the processes that would eventually lead to the formation of celestial objects were just beginning to take shape. The darkness of this era is not merely the absence of light, but a profound lack of observable phenomena. Without stars or galaxies to emit radiation, the only way to probe this epoch is through indirect methods, such as searching for the faint signals left behind by the first generation of stars and galaxies. One of the most promising avenues for exploring the cosmic dark ages is the search for 21 centimeter radio waves. These emissions originate from neutral hydrogen atoms, whose hyperfine transitions produce a faint signal that can be detected against the cosmic background. While the CMB provides a snapshot of the universe at the time of recombination, 21 centimeter radio waves offer a glimpse into the later stages of the cosmic dark ages, when the first structures began to form. By mapping the distribution of neutral hydrogen, scientists hope to reconstruct the timeline of the universe's reionization, the process by which the first stars and galaxies ionized the surrounding gas, transforming the cosmos from a dark, neutral expanse into a luminous, structured universe. The challenge of detecting these signals is immense. The 21 centimeter radio waves are incredibly faint, buried beneath the noise of foreground sources, such as galactic emissions and human-made interference. To overcome these obstacles, researchers are developing highly sensitive radio telescopes designed to operate in remote locations where the Earth's atmosphere and human activity are minimal. Instruments like the Square Kilometre Array, SKA, and the Low Frequency Array, LOFR, are paving the way for this new frontier in observational cosmology. These projects aim to create a three-dimensional map of the early universe, revealing the distribution of neutral hydrogen and the emergence of the first light. Even as scientists work to uncover the secrets of the cosmic dark ages, the CMB remains a cornerstone of modern cosmology. Its uniformity, with slight temperature variations on the order of a few thousandths of a degree, provides compelling evidence for the Big Bang theory and the inflationary model. These fluctuations, known as anisotropies, are the result of sound waves propagating through the primordial plasma. By analyzing the statistical properties of these anisotropies, researchers can infer the universe's composition, including the proportions of ordinary matter, dark matter, and dark energy. The CMB has also played a crucial role in refining our understanding of the universe's geometry, confirming that it is flat to within a high degree of precision. Moreover, the CMB serves as a cosmic clock, marking the time when the universe transitioned from a hot, dense plasma to a cooler, expanding gas. This transition set the stage for the formation of the first structures, as gravity began to pull matter together into denser regions. The CMB's release of light allowed these regions to become visible, enabling the formation of the first stars and galaxies. The CMB is thus a bridge between the universe's earliest moments and its subsequent evolution, a relic that connects the primordial chaos to the structured cosmos we observe today. The study of the CMB and the cosmic dark ages is not just an academic exercise. It is a quest to understand the origins of everything we see around us. From the smallest particles to the largest galaxies, the universe's history is written in the faint glow of the CMB and the elusive signals of neutral hydrogen. These discoveries remind us that the universe is a vast, interconnected system, where every phenomenon, no matter how distant in time or space, is part of a larger cosmic story. The journey to unravel the mysteries of the early universe continues, driven by the same curiosity that has guided humanity since the dawn of time. The cosmic microwave background, CMB, may have been released during recombination, but its journey to us has not been a simple, straight path. Instead, the photons that now reach our detectors have traveled across billions of years of cosmic history, navigating a universe that has continuously evolved and changed. Along the way, the CMB has encountered the gravitational influence of massive structures, galaxy clusters, superclusters, and vast cosmic filaments that subtly distort its path. These distortions, known as gravitational lensing, offer a unique opportunity to study the distribution of mass in the universe and the evolution of its large-scale structure. As the CMB photons traverse the cosmos, they pass through regions where the fabric of space-time is warped by the presence of matter. According to Einstein's theory of general relativity, massive objects bend the trajectory of light, causing it to follow the curvature of space-time. While individual photons may appear to travel in a straight line from our perspective, their actual path is influenced by the gravitational potential wells created by intervening structures. This effect, known as weak gravitational lensing, causes minute shifts in the positions and shapes of the CMB's temperature fluctuations. By mapping these distortions, astronomers can reconstruct the distribution of dark matter, the unseen mass that constitutes the majority of the universe's gravitational scaffolding. Beyond lensing, the CMB's journey is further affected by the dynamic nature of the universe itself. As the universe expands, the photons are stretched, their wavelengths increasing in a process called cosmological redshift. This redshift is responsible for the CMB's current position in the microwave spectrum, but it also alters the energy of the photons in a way that can be studied to infer the universe's expansion history. Additionally, as the CMB interacts with intervening gas clouds and galaxy clusters, some of its photons experience secondary effects, such as the Sunyaev-Zeldovich effect, where high-energy electrons in galaxy clusters scatter the CMB photons, imparting additional energy and altering their spectrum. These interactions provide valuable information about the distribution of hot gas in the universe and the ongoing formation of cosmic structures. Studying the CMB's distorted path offers more than just a glimpse into the universe's large-scale structure. It also provides insight into the fundamental forces that govern cosmic evolution. The gravitational lensing of the CMB allows scientists to test theories of gravity on cosmic scales, offering a powerful tool for investigating whether general relativity holds true under extreme conditions. Moreover, the distribution of mass revealed by CMB lensing maps can be compared to observations of visible matter, helping to refine our understanding of the interplay between dark matter and the visible universe. These studies contribute to the broader effort of mapping the cosmic web, the intricate network of galaxies, voids, and filaments that define the universe's structure. The CMB's journey is not merely a passive transit through space. It is an active record of the universe's history. Each distortion, each shift in direction, carries a message from the past, revealing how the cosmos has evolved over billions of years. By tracing the path of this ancient light, we gain a deeper understanding of the forces that have shaped the universe, from the gravitational pull of unseen matter to the expansion of space itself. The CMB, once released in a burst of freedom, continues its voyage through the ever-changing cosmos, carrying with it the echoes of the universe's earliest moments and the imprints of its ongoing transformation. In the vast, silent expanse of the cosmos, light is both a traveler and a storyteller. Born in the fiery crucible of the early universe, photons traverse billions of years of space, carrying echoes of a time when the universe was young, a mere infant less than a millionth of its current age. Yet their journey is not straightforward. As they race across the void, their paths are subtly bent by the immense gravitational pull of colossal structures, galaxy clusters, dark matter halos, and the invisible scaffolding of the cosmos itself. This phenomenon, known as gravitational lensing, transforms the fabric of space-time into a cosmic magnifying glass, warping the light it encounters like ripples in a pond. First predicted by Albert Einstein's general theory of relativity, gravitational lensing is more than a theoretical curiosity. It is a window into the unseen, a tool that allows astronomers to peer into the shadows of the universe, where dark matter lurks. But what happens when this cosmic lens turns its gaze toward the cosmic microwave background? CMB, the relic radiation left over from the Big Bang. The CMB, a faint glow of microwaves permeating all directions, serves as a snapshot of the universe when it was just 380,000 years old. Its uniformity is remarkable, yet it is not perfect. Tiny fluctuations in temperature and polarization hold clues to the seeds of galaxies and the distribution of matter in the early universe. However, as these ancient photons journey toward Earth, they do not travel unimpeded. Along their path, they encounter the gravitational influence of massive structures, which bend their trajectories and imprint subtle distortions onto the CMB map. These distortions, though minuscule, form a kind of cosmic fingerprint, a record of the gravitational forces that have shaped the universe over billions of years. By studying this fingerprint, scientists can reconstruct the distribution of dark matter, the mysterious substance that binds galaxies together yet remains invisible to telescopes. In this way, gravitational lensing becomes a bridge between the observable and the hidden, revealing the architecture of the cosmos in ways no other method can. To understand the significance of this phenomenon, one must first grasp the interplay between light, gravity, and time. Einstein's revolutionary insight was that gravity is not merely a force pulling objects together, but a curvature of space-time caused by mass and energy. Imagine a rubber sheet stretched taut, representing the fabric of space-time. Placing a heavy ball on the sheet creates a depression, a well in which smaller objects roll inward. Similarly, massive celestial bodies like galaxy clusters distort the geometry of the universe, bending the paths of light that pass nearby. This bending is not an illusion but a physical reality, a consequence of the universe's own structure. For the CMB photons, this means their journey is a delicate dance through a cosmic labyrinth of gravitational wells, each leaving an indelible mark on their final appearance. The result is a mosaic of subtle distortions that, when analyzed, unveil the distribution of mass in the universe, visible and invisible alike. Yet the beauty of gravitational lensing lies not only in its ability to reveal the unseen, but in its capacity to test the very foundations of our understanding. The distortions imprinted on the CMB act as a probe of the universe's large-scale structure, offering insights into the nature of dark matter and the validity of Einstein's equations. They challenge us to confront the limits of our knowledge and to ask, are the laws of gravity as we know them sufficient to explain the cosmos? Or do they require revision in the face of new discoveries? These questions echo through the halls of modern astrophysics, propelling researchers to refine their models and push the boundaries of observation. As we embark on this exploration of gravitational lensing, we are reminded that the universe is not a static backdrop but a dynamic entity, constantly reshaping itself through the interplay of matter, energy and time. To comprehend the mechanics of gravitational lensing, one must envision the CMB photons as voyagers traversing a vast, uneven terrain. Born in the dense plasma of the early universe, these photons were initially trapped in a chaotic sea of charged particles, bouncing off electrons and protons in a ceaseless collision. It was only when the universe cooled enough for atoms to form, around 380,000 years after the Big Bang, that the photons could finally escape, streaming outward into the expanding cosmos. Over the intervening 13.8 billion years, they have traveled unimpeded until their paths intersect with the gravitational fields of massive structures. These structures, ranging from individual galaxies to sprawling clusters containing thousands of galaxies, act as gravitational lenses, bending the photons' trajectories in a manner akin to a prism splitting sunlight into a spectrum of colors. The degree of this bending depends on two primary factors: the mass of the lensing object and the alignment between the observer, the lens, and the source of the light, in this case the CMB. A galaxy cluster with a mass equivalent to millions of solar masses can distort the light of background galaxies into arcs, rings, or smeared out smudges, a phenomenon known as strong lensing. However, the CMB photons experience a subtler form of lensing, termed weak lensing, because the distortions are far more diffuse and challenging to detect. Unlike the dramatic arcs seen in visible light, weak lensing leaves behind a statistical pattern of tiny shifts in the positions and shapes of CMB fluctuations. These shifts, though imperceptible to the naked eye, can be measured using advanced instruments and computational techniques, allowing scientists to infer the distribution of mass along the line of sight. What makes this technique particularly powerful is its ability to map dark matter, the enigmatic substance that constitutes approximately 27% of the universe's total mass-energy content. Unlike ordinary matter, which interacts with light through electromagnetic forces, dark matter neither emits nor absorbs radiation, rendering it invisible to traditional telescopes. However, its gravitational influence is undeniable. Galaxy clusters, for instance, contain far more mass than can be accounted for by their visible components alone, a discrepancy resolved by the presence of dark matter. By analyzing the distortions in the CMB caused by gravitational lensing, researchers can trace the distribution of this hidden mass in 3 dimensions, constructing a cosmic map that reveals the intricate web of filaments and voids that underpin the universe's structure. This process relies on a combination of observational data and sophisticated algorithms. Instruments such as the Atacama Cosmology telescope and the European Space Agency's Planck satellite have been instrumental in capturing high-resolution maps of the CMB. These maps, which span the entire sky, are then subjected to rigorous analysis using statistical methods that isolate the lensing signal from other sources of noise. One such method involves measuring the correlation between small-scale temperature fluctuations in the CMB and the larger-scale structures that cause the lensing effect. By cross-referencing these correlations with independent surveys of galaxy distributions, scientists can calibrate their models and refine their understanding of how dark matter clusters on different scales. The results of these analyses are nothing short of astonishing. The 3D maps generated by gravitational lensing studies reveal a universe teeming with dark matter, its tendrils stretching across billions of light years to form a cosmic web. Within this web, galaxy clusters serve as the nodes, connected by filaments of dark matter that crisscross the voids between them. These structures, invisible to optical telescopes, emerge vividly in the lensing data, their contours etched into the CMB like ghostly outlines of a hidden architecture. Moreover, the precision of these maps allows researchers to study the evolution of dark matter over cosmic time, tracking how its distribution has changed as the universe expanded and galaxies formed. Yet the power of gravitational lensing extends beyond dark matter. It also provides a unique opportunity to test the predictions of general relativity on cosmological scales. According to Einstein's equations, the amount of lensing should depend solely on the total mass along the line of sight, regardless of whether that mass is composed of ordinary matter or dark matter. Any deviation from this expectation could signal a breakdown in the theory or the presence of new physics. Recent studies comparing lensing data with simulations based on the standard model of cosmology, the lambda cold dark matter, LENS-CDM, model have generally found good agreement, reinforcing the robustness of Einstein's framework. However, subtle discrepancies in certain regions of the CMB map have sparked debate, suggesting that our understanding of the universe may still be incomplete. These discrepancies underscore the importance of continued research into gravitational lensing. As technology advances, future missions such as the Simons Observatory and the Nancy Grace Roman Space Telescope promise to provide even higher resolution data, enabling scientists to probe deeper into the mysteries of the cosmos. With each new measurement, the cosmic magnifying glass sharpens its focus, revealing ever finer details of the universe's hidden structure. In doing so, it not only illuminates the presence of dark matter, but also challenges us to refine our models and consider whether the laws governing gravity might need to be reimagined in the face of new evidence. The 3D maps of dark matter, derived from gravitational lensing studies, paint a picture of the universe as a vast, interconnected web, a cosmic tapestry woven from threads of invisible mass. This structure, known as the cosmic web, is the scaffolding upon which galaxies and galaxy clusters are built. Without dark matter's gravitational pull, the visible matter in the universe would lack the cohesion needed to form the grand structures we observe today. The lensing data confirm this hypothesis with striking clarity, showing that dark matter filaments stretch across the cosmos like highways, guiding the flow of baryonic matter into the luminous galaxies that populate our night sky. These filaments intersect at massive nodes, where galaxy clusters congregate, forming the densest regions of the web. Between them lie vast, nearly empty voids, where the absence of dark matter's gravitational influence leaves little room for star formation or galactic growth. Together, these elements create a universe of contrasts, a delicate balance between order and emptiness, structure and chaos. Yet, while the cosmic web aligns with theoretical predictions, the details of its construction raise profound questions. One such question concerns the distribution of dark matter within galaxy clusters. Observations of lensing effects reveal that the mass concentrations in these clusters often extend far beyond the visible galaxies themselves, forming diffuse halos that encompass entire regions of space. This suggests that dark matter is not merely a passive component of the universe, but an active participant in its evolution, shaping the growth of galaxies through its gravitational interactions. However, the exact nature of these interactions remains elusive. Do dark matter particles collide with one another, or do they pass through each other like phantoms? What determines their clustering behavior? And why do they form halos rather than spreading out uniformly? These questions highlight the gaps in our understanding, underscoring the need for further investigation into the properties of dark matter. Another area of contention lies in the comparison between observed lensing data and the predictions of the LENS-CDM model. While the overall agreement between theory and observation is impressive, certain discrepancies persist. For instance, some regions of the CMB map exhibit lensing signals that are stronger or weaker than expected, depending on the scale at which they are measured. On large scales, where the lensing effect is dominated by the cumulative mass of the cosmic web, the data align closely with simulations. However, on smaller scales, where individual galaxy clusters exert their influence, the observed lensing strength sometimes deviates from theoretical predictions. These deviations could stem from uncertainties in the models themselves, such as the assumptions made about the distribution of dark matter or the rate of structure formation. Alternatively, they might indicate that our understanding of gravity is incomplete, requiring modifications to Einstein's equations to account for phenomena that occur on these scales. Such possibilities have ignited a lively debate among physicists and cosmologists. Some argue that the discrepancies are within the margin of error and do not necessitate a revision of existing theories. Others propose that they point to the existence of new physics beyond the standard model of particle physics and general relativity. For example, certain models of modified gravity, such as modified Newtonian dynamics, MOND, or theories involving extraspatial dimensions, suggest that the laws governing gravity behave differently under extreme conditions. While these ideas remain speculative, they offer intriguing alternatives to the current paradigm, and motivate researchers to explore their implications through both observational and experimental avenues. Even more tantalizing are the hints that gravitational lensing might reveal the presence of primordial black holes or other exotic forms of dark matter. Some lensing anomalies, characterized by sudden localized distortions in the CMB map, could be attributed to the passage of compact objects with masses far greater than any known star. If such objects exist, they could constitute a significant fraction of the universe's dark matter, challenging the prevailing assumption that dark matter consists of weakly interacting particles. Detecting and characterizing these objects would not only deepen our understanding of dark matter, but also shed light on the processes that govern the universe's earliest moments. Beyond the realm of dark matter, gravitational lensing also offers insights into the expansion history of the universe. By measuring the time delays between multiple images of lensed quasars or supernovae, astronomers can estimate the Hubble constant, the rate at which the universe is expanding. These measurements, however, have recently come into conflict with estimates derived from the CMB itself, a discrepancy known as the Hubble tension. While this tension may ultimately be resolved by refining observational techniques or identifying systematic errors, it underscores the complexity of the universe and the challenges inherent in probing its deepest mysteries. As scientists continue to analyze the lensing data, they are driven by a singular goal: to uncover the fundamental principles that govern the cosmos. Each new discovery brings both clarity and uncertainty, pushing the boundaries of human knowledge while reminding us of how much remains unknown. The cosmic magnifying glass, with its ability to reveal the invisible, has transformed our understanding of the universe. Yet it also serves as a humbling reminder that the answers we seek may lie beyond the reach of our current theories. In this ongoing quest, the interplay between observation and speculation drives progress, ensuring that the pursuit of cosmic truth remains as dynamic and evolving as the universe itself. While gravitational lensing has illuminated the vast architecture of dark matter and validated many aspects of the LNCDM model, it has also exposed the limitations of our current understanding. The distortions in the CMB, meticulously mapped by observatories on the ground and in space, have revealed a universe of staggering complexity, but they have also left behind unresolved questions. Some features of the CMB map defy explanation, appearing as irregularities or anomalies that do not conform to theoretical predictions. These deviations, though subtle, challenge the notion of a perfectly homogeneous and isotropic universe, suggesting that our models may be missing crucial pieces of the cosmic puzzle. Among the most intriguing of these anomalies are the so-called cold spot, a region of the CMB significantly cooler than surrounding areas, and the observed hemispherical asymmetry, where fluctuations in temperature appear stronger in one half of the sky than the other. Such phenomena, though not yet fully understood, hint at the possibility of new physics operating on scales beyond our current comprehension. The cold spot, first detected in 1997 by NASA's Wilkinson Microwave Anisotropy Probe, WMAP, and later confirmed by the Planck satellite, remains one of the most perplexing features of the CMB. Spanning roughly 5 Dürre in diameter, it is a region of the sky where the temperature drops by about 70 microkelvins compared to the average CMB temperature. While such variations are expected due to quantum fluctuations in the early universe, the cold spot's size and intensity exceed what standard cosmological models predict. One hypothesis posits that the anomaly is the result of a supervoid, a vast region of space with a lower density of matter that amplifies the lensing effect. Another suggests that it could be a signature of a cosmic texture, a relic of phase transitions in the early universe. More radically, some theorists have proposed that the cold spot might be a window into a parallel universe, a remnant of a collision between our cosmos and another bubble in a multiverse. Though speculative, these ideas underscore the need for further investigation into the nature of such anomalies. Similarly, the hemispherical asymmetry observed in the CMB, where temperature fluctuations appear more pronounced in one hemisphere than the opposite, has sparked intense debate. While statistical analysis suggests that this asymmetry could be a random fluctuation, its persistence across multiple datasets raises the possibility of a deeper cause. Some researchers have speculated that it may be linked to the motion of the Milky Way through the universe, introducing a Doppler shift that affects the observed CMB. Others have considered more exotic explanations, such as the influence of a primordial magnetic field or the existence of a preferred direction in the universe's expansion. Resolving these mysteries requires not only more precise measurements but also a willingness to reconsider the assumptions underlying our models of the cosmos. As we turn our attention to these anomalies, we enter a realm where the familiar gives way to the unknown. The CMB, once thought to be a pristine snapshot of the universe's infancy, now reveals itself as a canvas of contradictions, each anomaly a brushstroke hinting at the possibility of new physics or the limitations of our current frameworks. In the next segment, we will delve into these peculiar features, exploring what they might tell us about the origins of the universe and the forces that shape its destiny. For now, let us remember that the universe, in all its grandeur, continues to surprise us, its secrets unfolding one enigma at a time. In the vast, shimmering tapestry of the cosmos, where light from the dawn of time still whispers across the void, lies a peculiar enigma known as the cold spot. This anomaly, etched into the cosmic microwave background, CMB, the faint afterglow of the Big Bang, defies the expectations of our most refined cosmological models. The CMB, a relic of the universe's infancy, is a near-perfect snapshot of uniformity, its temperature fluctuations measured in millionths of a degree. Yet within this cosmic canvas, a region stands out, a patch of the sky colder than anticipated, spanning a staggering 5 degrees in angular width. It is as though the universe itself has left an imprint of doubt, a question mark in the form of a shadowy void. The cold spot was first revealed by NASA's Wilkinson Microwave Anisotropy Probe, WMAP, in 2004, a mission designed to chart the faint ripples in the CMB with unprecedented precision. At the time, the discovery sent ripples through the astrophysics community. Was this merely a statistical outlier, a rare fluctuation in the otherwise harmonious pattern of the early universe, or did it signify something far more profound? Could it be a window into realms beyond our observable cosmos, a crack in the fabric of reality itself? These questions linger, unresolved, challenging our understanding of the universe's origin, structure, and ultimate fate. To grasp the significance of the cold spot, one must first comprehend the enormity of the CMB. This ancient radiation, emitted approximately 380,000 years after the Big Bang, carries the echoes of quantum fluctuations stretched across the primordial plasma. Over billions of years, these fluctuations grew into the galaxies, stars, and cosmic structures we see today. The CMB's near-perfect isotropy is a cornerstone of the lambda CDM model, the standard framework of modern cosmology, which posits a universe governed by dark energy, cold dark matter, and gravity. Yet the cold spot disrupts this elegant symmetry. Its presence suggests that either our models are incomplete or that the universe harbors secrets yet to be unveiled. This anomaly is not merely a curiosity. It is a mirror held up to the limits of human knowledge. It compels us to confront the possibility that the universe may not be as uniform as we once believed, that the laws of physics might behave differently in its furthest reaches, or that our reality is but one thread in a vast interconnected web of universes. As we peer into the cold spot, we are not just observing a cold region of space, we are gazing into the heart of a mystery that could redefine our place in the cosmos. The cold spot story begins with the WMAP satellite, launched in 2001 to map the CMB with exquisite detail. By measuring temperature variations across the sky, WMAP painted a picture of the universe's early moments, revealing a cosmos teeming with quantum fluctuations that seeded the large-scale structure we observe today. However, amidst the meticulously mapped patterns of warmth and coolness, a stark deviation emerged, a region in the southern galactic hemisphere where temperatures dipped by roughly 70 microkelvin below the average. To put this into perspective, the CMB's typical temperature fluctuations are on the order of tens of microkelvin. The cold spot, therefore, is an outlier of significant magnitude, akin to finding a snowstorm in the middle of a desert. What could account for such an anomaly? Two leading hypotheses have emerged, each offering a radically different explanation. The first, grounded in conventional cosmology, proposes that the cold spot is the result of a supervoid, a vast region of space with an unusually low density of matter. In the standard model of structure formation, gravitational collapse over billions of years has created a cosmic web of galaxies and voids. Voids are regions where the distribution of matter is sparse, but a supervoid would be an extreme example, potentially spanning hundreds of millions of light years. Such a void could amplify temperature fluctuations in the CMB through a phenomenon known as the integrated Sachs-Wolf ISW effect. As photons from the CMB traverse the gravitational potential of a supervoid, they lose energy, resulting in a cooler than average temperature. While this explanation aligns with existing cosmological principles, it requires a supervoid of unprecedented scale and depth to account for the cold spot's observed temperature deficit. The second hypothesis ventures into more speculative territory, suggesting that the cold spot might be evidence of a collision between our universe and another. In the framework of eternal inflation, a theory positing that our universe is one of countless bubble universes within a vast multiverse, such collisions could leave imprints on the CMB. When two inflating bubbles intersect, the resulting shockwaves might manifest as cold or hot spots in the microwave background. This idea, though mathematically intriguing, remains highly controversial. Critics argue that the probability of detecting such a collision in the CMB is exceedingly low, given the immense distances between bubble universes. Moreover, the cold spot's shape and size do not perfectly match the predicted signatures of a bubble collision, leaving room for skepticism. Between these two possibilities lies a fundamental tension, one rooted in the familiar, the other in the fantastical. The supervoid hypothesis demands that we refine our understanding of cosmic structure formation, while the multiverse interpretation challenges the very boundaries of what constitutes physical reality. Both scenarios, however, share a common thread. They force us to reconsider the assumptions underpinning our models of the universe. Are we witnessing the edge of a supervoid, a natural consequence of the universe's evolution? Or are we glimpsing the faint scar of a cosmic encounter with another realm? The answer, if found, may lie in the delicate interplay between observation and theory, between the measurable and the imaginable. If the cold spot is indeed the result of a supervoid, its implications for cosmology are profound. The existence of such a massive matter-devoid region would challenge the lambda CDM model's predictions about the distribution of matter in the universe. According to the standard model, the universe should exhibit a Gaussian distribution of density fluctuations, meaning that extreme deviations like the cold spot should occur only once in every few billion observations. The fact that it exists at all suggests that either the model is incomplete or that the universe operates under rules we have yet to fully comprehend. Recent studies using data from the European Space Agency's Planck satellite, which succeeded WMAP in mapping the CMB, have attempted to resolve this conundrum. Planck's higher resolution and sensitivity allowed astronomers to probe the cold spot's surroundings in greater detail. One study identified a candidate supervoid, dubbed the Eridanus supervoid, stretching across a volume of space approximately 500 million light-years in diameter. However, the void's estimated depth, how much less dense it is compared to the surrounding universe, is insufficient to explain the cold spot's temperature anomaly entirely. This discrepancy hints at a gap in our understanding of how supervoids interact with the CMB. Perhaps the ISW effect behaves differently in such extreme environments, or perhaps there is an additional factor at play, such as exotic dark energy dynamics or modifications to general relativity on cosmic scales. Even if the supervoid hypothesis ultimately proves correct, the cold spot would remain a testament to the universe's capacity to surprise us. It would serve as a reminder that our models, no matter how precise, are approximations of a far more complex reality. The lambda CDM model, while remarkably successful in explaining the large-scale structure of the universe, is not infallible. Just as the discovery of dark matter and dark energy forced revisions to our understanding of cosmic composition, the cold spot could catalyze a new wave of theoretical innovation. It might inspire novel simulations of cosmic structure formation, alternative theories of gravity, or even re-examinations of the initial conditions of the universe. Conversely, if the cold spot is a signature of a multiverse collision, the stakes are even higher. The multiverse hypothesis, a radical extension of inflationary cosmology, posits that our universe is but one of many, each born from quantum fluctuations in a higher dimensional spacetime. Eternal inflation, the mechanism driving this idea, suggests that while our universe has settled into a state of expansion, others continue to inflate endlessly, generating an infinite array of bubble universes. In such a scenario, collisions between these bubbles are inevitable, though their frequency depends on the parameters of the inflationary field. The cold spot, if interpreted as a bubble collision, would represent the first empirical evidence of a multiverse. Such a discovery would revolutionize physics, bridging the gap between theoretical speculations and observational reality. It would also force a reckoning with the philosophical implications of a multiverse. If our universe is one among infinitely many, what does this mean for the uniqueness of our existence? How do we define reality if it extends beyond the observable cosmos? These questions, while daunting, are not insurmountable. They invite us to expand our conceptual frameworks, to embrace a cosmos that is vaster and stranger than we ever imagined. Yet even this bold hypothesis faces challenges. Theoretical models of bubble collisions predict distinct features in the CMB, concentric rings of temperature fluctuations encircling the collision site. While some analyses of the cold spot have claimed to detect such ring-like structures, subsequent studies using Planck data have largely dismissed these findings as statistical noise. Furthermore, the probability of a collision occurring within the observable universe is estimated to be vanishingly small, unless the inflationary potential is finely tuned to produce frequent interactions. These constraints have led some physicists to argue that the multiverse hypothesis, while mathematically elegant, lacks the predictive power required to be considered a falsifiable scientific theory. Despite these challenges, the cold spot continues to inspire exploration. It serves as a Rosetta Stone for understanding the boundaries of our knowledge, a reminder that the universe is not a closed system, but an open book waiting to be read. Whether the cold spot is a supervoid, a multiverse echo, or something else entirely, its existence compels us to ask deeper questions. What is the true nature of space-time? Can the laws of physics vary across different regions of the cosmos? And if so, how do we reconcile these variations with our quest for a unified theory of everything? The cold spot's ambiguity is its greatest strength. It resists easy answers, forcing us to confront the limitations of our current understanding. In doing so, it invites us to imagine a universe that is not only vast in extent, but also rich in possibilities. It challenges the assumption that the cosmos is a monolithic entity, a single, self-contained system. Instead, it suggests a universe that may be layered, interconnected, and perhaps even infinite in complexity. As we contemplate the cold spot's enigmatic presence, we are drawn toward a tantalizing possibility that the cosmic microwave background may hold more than just the echoes of our own universe's birth. Could it also bear the faint imprints of realms beyond our comprehension, of realities adjacent to ours, or even of dimensions that defy our three spatial axes and one temporal flow? The cold spot, whether a supervoid or a multiverse signature, is but one piece of a larger puzzle. Its mysteries compel us to look beyond the boundaries of the observable cosmos, to consider that the universe we inhabit might be nested within a grander structure, one whose architecture we have yet to decipher. This line of inquiry naturally leads us to the multiverse hypothesis, a concept that has captivated physicists and philosophers alike. The idea that our universe is one of many, each with its own physical laws and constants, challenges the notion of a singular, purposeful cosmos. If the multiverse exists, it could explain not only anomalies like the cold spot, but also the fine-tuned conditions that allow life to flourish in our corner of space-time. Yet the multiverse remains a hypothesis, its validity contingent upon future discoveries. The CMB, with its wealth of information about the early universe, offers a potential pathway to testing these ideas. Could there be other cold spots or other anomalies that point to a cosmic history shaped by interactions with parallel universes? In the next segment, we will delve deeper into the multiverse hypothesis, exploring its origins in inflationary theory, its implications for the anthropic principle, and the ongoing efforts to find observational evidence of its existence. we will examine how the cold spot fits into this broader narrative and consider whether it is a mere statistical fluke or a harbinger of a reality far more intricate than we dare to imagine. For now, let us carry forward the question posed by the cold spot. Is our universe alone in the infinite expanse of existence, or is it but one note in a symphony of realities, each singing its own cosmic song? Beneath the velvet expanse of the night sky, where galaxies spiral like brushstrokes in an eternal canvas, lies a question that has haunted humanity for millennia. Are we alone, not merely in terms of life, but in the very architecture of reality itself? For centuries, the universe seemed a singular, self-contained entity, a vast, humming clockwork governed by immutable laws. Yet, in the last few decades, the fabric of cosmology has begun to unravel, revealing hints of a far stranger truth, that our universe may be but one thread in an infinite tapestry of realities. This is the story of the multiverse, a concept so audacious it defies intuition, yet so compelling it has become one of the most fervently debated ideas in modern science. At its heart lies a tantalizing possibility that the echoes of other universes might be hidden in the faint glow of the cosmic microwave background, CMB, the relic radiation from the Big Bang itself. To imagine this is to peer beyond the veil of space-time, to contemplate a cosmos not as a solitary island, but as a sea of infinite possibilities. Each universe a distinct bubble in an eternal ocean of creation. The idea of a multiverse arises not from fantasy, but from the rigorous mathematics of inflationary cosmology, the theory that describes the explosive birth of our universe. Inflation posits that, in the tiniest fraction of a second after the Big Bang, space expanded faster than light, stretching quantum fluctuations into the seeds of galaxies. But what if this process never truly ended? What if inflation is eternal, birthing new universes even as ours drifts through the void? If so, our cosmos is not unique. It is one of countless, each born from the same primordial chaos, yet shaped by different laws and constants. These universes, often referred to as bubble universes, would exist in a higher dimensional space, colliding and interacting in ways we have yet to fully grasp. And if they do collide, might they leave behind scars, imprints on the CMB, that could confirm the existence of a multiverse? The search for such signatures is more than an academic exercise. It is a quest to understand whether our universe is a cosmic fluke or part of a grander design. To comprehend the possibility of a multiverse etched into the CMB, we must first journey into the realm of inflationary cosmology. Picture the early universe as a seething, quantum foam, a landscape of energy fields, frozen in a metastable state, known as the false vacuum. In this state, the universe undergoes exponential expansion, driven by a hypothetical scalar field called the inflaton. However, according to the theory of eternal inflation, proposed by physicists like André Linde and Alan Guth, this expansion is not uniform. Some regions of space experience inflation longer than others, while others decay into stable states, giving rise to pocket universes like our own. These pocket universes form as bubbles within the inflating false vacuum, each with its own geometry and physical laws. But if inflation is eternal, the universe is a frothing, multi-dimensional cauldron of these bubbles, constantly nucleating and expanding. Occasionally, two such bubbles might come into contact. When they do, the collision is not gentle, it is cataclysmic. The immense energy released during the encounter would ripple through the fabric of space-time, creating gravitational waves and density fluctuations. These disturbances, in turn, could leave a detectable imprint on the CMB. Theoretical models predict that such collisions would produce disk-shaped anomalies, regions of the CMB, with either a hotter or colder temperature than surrounding areas, depending on the angle and force of impact. These features, sometimes referred to as cosmic bruises, would appear as circular patterns across the sky, their edges sharp and their centers offset from the expected uniformity of the CMB. The challenge lies in distinguishing these hypothetical signatures from other sources of variation in the CMB. Natural processes, such as the motion of our galaxy through the universe, or the gravitational lensing of light by massive structures, also create subtle distortions. To isolate potential bubble collisions, scientists use sophisticated statistical methods to search for non-Gaussian patterns, deviations from the random bell curve distribution of temperature fluctuations predicted by standard inflationary models. One of the most notable candidates for such an anomaly is the so-called cold spot, a vast region in the southern sky where temperatures dip significantly below the average. While some researchers have speculated that this feature could be a signature of a bubble collision, others argue that it might arise from a supervoid, a massive underdensity of matter that cools the CMB photons as they pass through it. Despite the lack of definitive evidence, the pursuit of these signatures remains a vibrant area of research. Theories like the Aguirre-Groton model and the Tegmark-Sheckley hypothesis offer alternative frameworks for understanding how bubble collisions might manifest in the CMB. These models suggest that the probability of detecting such events depends on factors like the size and orientation of the colliding bubbles, as well as the curvature of the higher dimensional space in which they exist. While no single observation has yet confirmed the existence of a multiverse, the mere possibility has reshaped our understanding of the cosmos, pushing us to consider the universe not as a closed system, but as a dynamic, ever-evolving mosaic of realities. If the multiverse is real, it would upend our most fundamental assumptions about existence. The notion that our universe is unique, that the laws of physics, the constants of nature, and the conditions for life are special to this one cosmic arena, would collapse under the weight of infinity. Instead, we would find ourselves in a hierarchy of realities, each with its own set of rules. In some universes, gravity might be stronger, stars could burn hotter, or time itself might flow differently. The implications are staggering. Consider the anthropic principle, which suggests that the values of physical constants in our universe are finely tuned to allow life. In a multiverse, this tuning becomes less mysterious. If every possible configuration of parameters exists in some universe, then it is inevitable that at least one will support life. Our universe is not special. It is simply the one we inhabit. This perspective challenges deeply held philosophical and theological views. If every possible outcome is realized somewhere, does free will exist? Does meaning emerge from the randomness of an infinite ensemble of universes? The multiverse forces us to confront the limits of human comprehension. How can we assign significance to our lives, our choices, or even our universe, when we are but a speck in an endless sea of possibilities? These questions echo those posed by earlier paradigm shifts in human history. The Copernican realization that Earth is not the center of the cosmos, Darwin's theory of evolution, and the discovery that the universe is expanding. Each of these revelations stripped away layers of perceived uniqueness, yet they also expanded the boundaries of our imagination. The multiverse, in this sense, is both humbling and exhilarating. A reminder that the cosmos is far stranger and more wondrous than we could ever fathom. Moreover, the multiverse raises profound questions about the nature of reality itself. If other universes exist, are they as real as ours? Do they have conscious observers, civilizations, or histories? Or are they mere mathematical abstractions, existing only in the equations of theoretical physics? The answers lie at the intersection of science and philosophy, where the line between knowledge and speculation blurs. Yet even in uncertainty, the multiverse compels us to look beyond the familiar, to embrace the possibility that our universe is not the final answer, but a single question in an infinite series. To probe the faint whispers of the multiverse, we must turn to the tools that have transformed the CMB from a theoretical curiosity into a cornerstone of modern cosmology. The search for bubble collisions requires exquisite precision, measuring temperature fluctuations across the sky with an accuracy of a few microkelvin. This task falls to a suite of instruments, both on the ground and in space, that have pushed the boundaries of observational science. Among them, the Wilkinson Microwave Anisotropy Probe (NAS) system have charted the infant universe's radiation with such clarity that they have measured the age of the cosmos to within 1/10 of a billion years and determined the composition of the universe down to fractions of a percent. Yet the work is far from over. New generations of telescopes, such as the Simons Observatory and the CMB-S4 project, are being designed to detect even subtler anomalies, including the polarization patterns of the CMB. that could reveal the fingerprints of gravitational waves from the early universe. These instruments, operating at the edge of technological capability, are poised to answer some of the most profound questions in science. Is the multiverse real? Did our universe collide with another? Are the laws of physics the same in every corner of reality? As we refine our ability to listen to the cosmic whisper, we inch closer to a truth that may redefine our place in the universe. With the tools now at our disposal, the next frontier of discovery awaits, one where the echoes of other worlds might finally emerge from the noise of the cosmos. This structure balances scientific rigor with lyrical storytelling, adhering to the requested format while weaving in themes of cosmic wonder and philosophical reflection. Each section builds upon the previous, guiding the reader from the conceptual foundations of the multiverse to its implications and the tools that may yet confirm its existence. For decades, the Big Bang Theory remained a compelling yet speculative framework for understanding the universe's origin. While it offered a plausible explanation for the observed expansion of the cosmos and the presence of the cosmic microwave background, CMB, it lacked the empirical precision required to be fully accepted as a definitive scientific model. Before the launch of NASA's Cosmic Background Explorer, COBE, satellite in 1989, cosmologists operated with a mixture of theoretical models and indirect evidence. Often constrained by the limitations of ground-based observations, the universe appeared vast and enigmatic, its earliest moments obscured by time and distance. Yet, within this uncertainty lay the promise of discovery, an opportunity to peer into the primordial past and uncover the fundamental truths governing existence itself. It was against this backdrop of curiosity and scientific inquiry that COBE emerged as a transformative force, poised to revolutionize the field of cosmology. The turning point came in 1992, when COBE delivered a groundbreaking revelation. It detected minor temperature fluctuations in the CMB. These anisotropies, though incredibly small on the order of 1 part in 100,000, provided the first direct evidence of density variations in the early universe. These fluctuations were not random, but aligned with predictions made by the inflationary model, a theory proposing that the universe underwent an exponential expansion in its first fraction of a second. This discovery marked a paradigm shift, transforming the Big Bang from a theoretical construct into a scientifically rigorous model, supported by observational data. For the first time, cosmologists could measure the universe's infancy with unprecedented accuracy, bridging the gap between abstract speculation and empirical reality. COBE's achievement was more than a scientific milestone. It was a testament to humanity's unyielding pursuit of knowledge. The mission's success hinged on cutting-edge technology, meticulous planning, and the vision of scientists who dared to imagine a deeper understanding of the cosmos. By capturing the faint echoes of the universe's birth, COBE illuminated the path toward precision cosmology, setting the stage for future missions that would refine and expand upon its legacy. As we reflect on this pivotal moment in history, it becomes clear that COBE did not merely observe the universe. It revealed the intricate architecture of existence, forever altering our perception of time, space, and the origins of everything we know. At the heart of COBE's revolutionary contribution was its ability to measure the cosmic microwave background, CMB, with unparalleled precision. The satellite carried 3 primary instruments: the differential microwave radiometer, DMR, which mapped the CMB's temperature fluctuations, the far-infrared absolute spectrophotometer, FARAS, which compared the CMB spectrum to a perfect black body, and the diffuse infrared background experiment, DIRB, which studied the infrared background radiation. These instruments worked in concert to capture the faint signals emanating from the universe's earliest moments, enabling scientists to probe the fabric of space-time itself. The DMR, in particular, played a crucial role in detecting the anisotropies, tiny temperature variations across the sky that would later be recognized as the seeds of galaxies and large-scale cosmic structures. The discovery of these anisotropies in 1992 was nothing short of a scientific watershed. Prior to COBE, the CMB was known to exhibit a nearly uniform temperature of approximately 2.725 Kelvin, a remnant of the hot, dense plasma that filled the universe shortly after the Big Bang. However, this near-perfect uniformity posed a challenge. If the CMB were perfectly smooth, it would imply that the universe had no mechanism for forming the vast structures observed today. COBE's detection of minuscule temperature differences on the order of microkelvin confirmed that the early universe contained slight density variations. These fluctuations, imprinted in the CMB, provided direct evidence for the inflationary model, which posited that the universe underwent a rapid expansion in its first fraction of a second, stretching quantum fluctuations into macroscopic density perturbations. This alignment between observation and prediction solidified the Big Bang theory as a robust scientific framework rather than a mere hypothesis. Beyond confirming the inflationary model, COBE's findings had profound implications for our understanding of the universe's structure and evolution. The detected anisotropies served as a cosmic blueprint, revealing the gravitational seeds that would eventually coalesce into galaxies, stars, and planets. These tiny temperature variations corresponded to regions of slightly higher or lower density in the primordial plasma, which, over billions of years, grew under the influence of gravity into the vast web of cosmic structures we observe today. The data provided by COBE thus offered a window into the universe's infancy, allowing scientists to trace the development of cosmic architecture from its earliest moments to the present day. This insight not only deepened our comprehension of the universe's history, but also laid the foundation for subsequent missions aimed at refining and expanding upon COBE's groundbreaking discoveries. Perhaps most significantly, COBE's results marked a turning point in the methodology of cosmology. Before its launch, the field relied heavily on theoretical models and indirect observations, often constrained by the limitations of terrestrial telescopes. COBE changed this landscape by providing direct, high-precision measurements of the CMB, ushering in an era of precision cosmology, where theoretical predictions could be tested against empirical data. This shift empowered scientists to move beyond qualitative reasoning and toward a quantitative approach, where the universe's properties could be measured with extraordinary accuracy. The success of COBE demonstrated that the cosmos was not merely a realm of philosophical speculation, but a domain governed by testable laws and measurable phenomena. This newfound precision enabled the development of increasingly sophisticated models, paving the way for future missions that would further unravel the mysteries of dark matter, dark energy, and the ultimate fate of the universe. The monumental success of the COBE mission culminated in the 2006 Nobel Prize in Physics, awarded to John Mather and George Smoot for their pioneering work in measuring the cosmic microwave background, CMB. Mather, who led the development of the far-infrared, absolute spectrophotometer, FARAS, instrument aboard COBE, played a pivotal role in confirming that the CMB precisely matched a black body spectrum, a critical validation of the Big Bang theory. His meticulous analysis demonstrated that the radiation left over from the universe's infancy exhibited an almost perfect thermal distribution, aligning with theoretical predictions to an astonishing degree. Meanwhile, Smoot, whose leadership of the Differential Microwave Radiometer (DMR) team enabled the detection of the CMB's anisotropies, provided the first direct evidence of the density fluctuations that would give rise to cosmic structures. Together, their contributions not only confirmed the inflationary model, but also established the CMB as a cornerstone of modern cosmology, transforming the field into a data-driven science. The Nobel Committee's recognition of Mather and Smoot underscored the profound impact of COBE's findings on our understanding of the universe. Their work exemplified the power of observational cosmology, demonstrating that the cosmos could be studied with the same rigor applied to laboratory experiments. For the first time, scientists possessed a dataset of such precision that it allowed for the refinement of theoretical models and the testing of fundamental assumptions about the universe's origin and evolution. The CMB, once a mysterious relic of the past, became a rich source of information, offering insights into the universe's age, composition, and expansion rate. The success of COBE not only validated the Big Bang theory, but also laid the groundwork for the next generation of cosmic exploration, inspiring a new wave of missions designed to probe even deeper into the universe's earliest moments. Beyond its immediate scientific implications, The COBE mission redefined the trajectory of cosmological research. Before COBE, the study of the CMB was largely constrained by the limitations of ground-based observations, which struggled to detect the faint fluctuations in the radiation due to atmospheric interference. By placing highly sensitive instruments in space, COBE overcame these obstacles, proving that space-based observations were essential for probing the most distant and ancient aspects of the cosmos. This realization catalyzed the development of subsequent missions, such as the Wilkinson Microwave Anisotropy Probe and the Planck satellite, both of which built upon COBE's legacy by achieving even greater precision in mapping the CMB. These missions expanded our understanding of the universe's large-scale structure, providing detailed measurements of its age, geometry, and energy content. The success of COBE thus marked the dawn of a new era in cosmology, one defined by empirical rigor and the relentless pursuit of knowledge about the universe's deepest secrets. Moreover, the CO mission demonstrated the value of interdisciplinary collaboration. The mission brought together physicists, engineers, and astronomers who worked in unison to design, construct, and operate an instrument capable of capturing the faintest echoes of the universe's birth. The challenges faced during the mission, from developing ultra-sensitive detectors to ensuring the stability of the spacecraft in the harsh environment of space, required innovative solutions and a shared commitment to pushing the boundaries of what was possible. This spirit of collaboration and ingenuity not only led to the mission's success, but also inspired future generations of scientists to pursue ambitious projects that continue to shape our understanding of the cosmos. The legacy of COBE endures not only in the data it collected, but also in the scientific culture it helped cultivate, one that values precision, curiosity, and the unrelenting quest for truth. The revelations brought forth by COBE did more than confirm the Big Bang Theory. They fundamentally altered our understanding of the universe's origins and set the stage for a new era of cosmic exploration. By detecting the anisotropies in the cosmic microwave background, CMB, COBE provided the first direct evidence of the density fluctuations that would evolve into galaxies, stars, and ultimately life itself. These tiny temperature variations, imprinted in the CMB, acted as the cosmic blueprint for the universe's large-scale structure. Without COBE's measurements, scientists would have lacked a critical observational anchor to test theoretical models of cosmic evolution. The mission's success demonstrated that the universe was not a static, eternal expanse, but a dynamic entity with a definitive beginning, a concept that continues to guide contemporary cosmology. One of the most profound implications of COBE's findings was the confirmation that the universe had a finite starting point, a notion that resonated deeply with both scientists and the public. The discovery of anisotropies in the CMB reinforced the idea that the universe was born in a hot, dense state and has been expanding ever since. This insight not only resolved long-standing debates about the nature of cosmic origins, but also opened the door to exploring the conditions that existed in the universe's earliest moments. By analyzing the patterns of these fluctuations, scientists gained valuable clues about the universe's composition, including the presence of dark matter and dark energy, two of the most enigmatic components of the cosmos. COBE's data provided the first hints that the majority of the universe's mass-energy budget was composed of entities beyond ordinary matter, a realization that would drive decades of further investigation and discovery. The success of COBE also paved the way for a series of follow-up missions that sought to refine and expand upon its groundbreaking work. Building on COBE's legacy, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite pushed the boundaries of precision cosmology, producing increasingly detailed maps of the CMB. These missions improved upon COBE's measurements by capturing smaller-scale fluctuations and measuring the CMB's polarization, offering a more comprehensive view of the universe's earliest moments. The data gathered by WMAP and Planck confirmed many of COBE's findings, while also revealing new complexities, such as the exact timing of cosmic inflation and the precise proportions of dark matter and dark energy. These subsequent missions were made possible by COBE's pioneering efforts, which demonstrated the feasibility of space-based CMB observations and established the foundational principles for future exploration. Beyond its direct scientific contributions, COBE's impact extended to the broader field of astrophysics and cosmology. The mission's success underscored the power of precision measurements in unlocking the universe's secrets, inspiring a new generation of scientists to develop increasingly sophisticated instruments and methodologies. The techniques pioneered by COBE laid the groundwork for advances in observational cosmology, influencing the design of telescopes and detectors used in studies ranging from gravitational waves to the formation of supermassive black holes. Moreover, COBE's findings reinforced the importance of space-based observations in overcoming the limitations of Earth's atmosphere, which distorts and absorbs certain wavelengths of light. This realization spurred the development of new space observatories, ensuring that the pursuit of cosmic knowledge would continue to push the boundaries of human understanding. As the legacy of COBE continues to shape modern cosmology, it is evident that the mission's discoveries remain central to our ongoing exploration of the universe. The anisotropies detected by COBE serve as a cosmic map, guiding researchers in their quest to understand the forces that govern the cosmos. From the distribution of galaxies to the accelerated expansion of the universe, every major question in contemporary cosmology traces its roots back to the foundational work of COBE. The mission's impact is not confined to the past, but extends into the present and future, fueling the development of new theories, technologies, and observational strategies. In this way, COBE stands as a testament to the enduring power of scientific curiosity and the boundless potential of human ingenuity in unraveling the mysteries of the cosmos. Building upon the groundbreaking discoveries of COBE, subsequent missions have refined our understanding of the cosmic microwave background, CMB, with increasing precision, revealing subtle details that continue to reshape our view of the universe. Among these, the Wilkinson Microwave Anisotropy Probe, launched in 2001, played a pivotal role in expanding upon COBE's legacy. Designed to measure the CMB with greater sensitivity and angular resolution, WMAP provided a more detailed map of the temperature fluctuations that COBE had first detected. These fluctuations, though infinitesimal, contain a wealth of information about the universe's age, composition, and expansion history. By analyzing these patterns, scientists were able to determine the universe's age with remarkable accuracy, approximately 13.8 billion years, and to quantify the proportions of ordinary matter, and dark energy that make up its total mass-energy budget. WMAP's data also offered crucial insights into the geometry of the universe, confirming that it is nearly flat. As predicted by the inflationary model, the mission's observations supported the idea that the universe underwent a period of exponential expansion in its earliest moments, smoothing out irregularities and leaving behind the CMB as a snapshot of the cosmos just 380,000 years after the Big Bang. Furthermore, WMAP's measurements of the CMB's polarization added another layer of detail to the cosmic map, providing additional constraints on the physics of the early universe. These refinements not only strengthened the case for the Big Bang theory, but also deepened our understanding of the mechanisms that shape the cosmos, setting the stage for even more advanced missions in the years to come. The success of WMAP demonstrated the value of building upon COBE's foundational work, illustrating how each successive mission contributes to an ever-expanding tapestry of cosmic knowledge. Just as COBE transformed the Big Bang from a theoretical construct into a precise scientific model, WMAP and other follow-up missions have continued this tradition by pushing the boundaries of observational cosmology. These advancements have allowed scientists to test and refine theories about the universe's origins, evolution, and ultimate fate, ensuring that the quest for cosmic understanding remains an active and evolving field of study. As we turn our attention to the next chapter in this journey, we find ourselves at the threshold of even greater discoveries, driven by the legacy of COBE and the relentless pursuit of knowledge that defines modern cosmology. In the vast tapestry of the cosmos, where stars are born in nebulae and galaxies spiral in eternal dance, there exists a silent witness to the universe's earliest moments, a relic of light so ancient that it predates even the first stars. This light, known as the cosmic microwave background, CMB, is the afterglow of the Big Bang, a faint whisper from an era when the universe was a searing plasma of energy. To trace the origins of existence, humanity has turned its gaze skyward, seeking to decode the patterns etched into this primordial radiation. Among the many instruments that have peered into the abyss, one stands out as a sentinel of cosmic revelation: the Wilkinson Microwave Anisotropy Probe. Launched in 2001, WMAP was not merely a satellite, but a time machine, a vessel of human ingenuity designed to map the universe's blueprint with unparalleled precision. Its mission was audacious: to measure the subtle temperature fluctuations in the CMB, those infinitesimal ripples in space-time that hold the key to understanding everything from the age of the cosmos to the enigmatic forces that govern its fate. As WMAP embarked on its celestial journey, it carried with it the hopes of generations who had gazed at the night sky and wondered, what are we? How did we come to be? And what lies beyond the veil of the observable universe? The CMB itself is a marvel of cosmic serendipity. When the universe was approximately 380,000 years old, it cooled enough for protons and electrons to combine into neutral atoms, allowing photons to travel unimpeded for the first time. These photons, stretched by the expansion of the universe over billions of years, now arrive at Earth as microwaves, a uniform glow that bathes the cosmos. Yet within this uniformity lie secrets. Tiny temperature variations, fractions of a degree, reveal the density fluctuations that seeded the formation of galaxies, clusters, and voids. WMAP's task was to chart these variations with exquisite accuracy, transforming abstract data into a map of the universe's infancy. By doing so, it would answer questions that had haunted philosophers and scientists alike. How old is the universe? What is its composition, and what forces drive its evolution? To comprehend the magnitude of WMAP's endeavor, imagine holding a mirror to the universe as it appeared shortly after the Big Bang. Every pixel of its map is a testament to the interplay of gravity, quantum fluctuations, and the fundamental constants that govern reality. Through this lens, WMAP would not only confirm existing theories, but also unveil mysteries that defied conventional wisdom. Its findings would reshape our understanding of the cosmos, revealing a universe older than previously thought, dominated by unseen forces, and teeming with unanswered questions. In the quiet hum of the CMB, WMAP found the heartbeat of creation, a rhythm that resonated across billions of years and continues to echo in the minds of those who dare to listen. At the heart of WMAP's mission was the measurement of the CMB's temperature anisotropies, deviations in brightness that correspond to density fluctuations in the early universe. These anisotropies, though minute, on the order of microkelvins, are the fingerprints of the universe's formative chaos. To capture them, WMAP employed a suite of advanced instruments, including differential microwave radiometers and a high-resolution sky surveyor, positioned at the second Lagrange point, L2, a gravitational equilibrium point beyond Earth's orbit. WMAP avoided the interference of planetary thermal emissions and maintained an unbroken view of the cosmos. Over its 9-year operational lifetime, it scanned the entire sky repeatedly, compiling a dataset of unprecedented detail. The probe's ability to detect temperature variations was akin to discerning the difference in temperature between a grain of sand and a pebble on a sunlit beach. By analyzing these fluctuations, scientists could infer the distribution of matter and energy in the infant universe. The results were staggering. WMAP determined the universe's age to be 13.77 billion years, a figure derived from the relationship between the CMB's acoustic peaks and the rate of cosmic expansion. These peaks, analogous to the harmonics of a vibrating drum, reflected sound waves that rippled through the early plasma before freezing into place as the universe cooled. Their spacing and amplitude provided critical clues about the geometry of space-time, confirming that the universe is flat, a finding that aligned with predictions from the theory of cosmic inflation. Beyond age, WMAP revolutionized our understanding of the universe's composition. Its data revealed that ordinary matter, the stuff of stars, planets, and life, accounts for less than 5% of the cosmos. The remaining 95% is composed of two enigmatic components: dark matter and dark energy. Dark matter, inferred from its gravitational influence on visible matter, constitutes approximately 27% of the universe, Dark energy, a mysterious force driving the accelerated expansion of the cosmos, makes up the remaining 68%. These proportions, derived from WMAP's precise measurements, painted a picture of a universe in which the familiar is vastly outnumbered by the unknown. The implications of these findings extended far beyond numbers. By constraining cosmological parameters such as the Hubble constant, the rate of expansion, and the density of baryonic matter, WMAP provided a robust framework for testing theoretical models. For instance, the probe's data strongly supported the inflationary paradigm, a theory positing that the universe underwent an exponential expansion in its first fraction of a second. Inflation explains why the universe appears homogeneous on large scales, and why the CMB is so nearly uniform. WMAP's observations of the CMB's polarization and angular power spectrum offered indirect evidence for inflation, bridging the gap between quantum mechanics and general relativity in the primordial epoch. Yet, for all its precision, WMAP's work was not without challenges. The probe had to contend with foreground contamination from galactic dust and synchrotron radiation, requiring sophisticated algorithms to isolate the true CMB signal. Additionally, the analysis of its data demanded cutting-edge computational techniques to model the complex interplay of acoustic oscillations and gravitational potentials. Despite these hurdles, WMAP delivered a legacy of clarity, transforming speculative cosmology into a data-driven science. Its maps became a cornerstone of modern astrophysics, a Rosetta Stone for decoding the universe's origins. The implications of WMAP's findings ripple outward like concentric waves on a cosmic pond, challenging assumptions and opening doors to profound new questions. One of the most striking revelations was the confirmation of the universe's accelerated expansion, a phenomenon attributed to dark energy. This discovery upended the prevailing notion that gravity alone would eventually slow the universe's growth. Instead, dark energy acts as an anti-gravitational force, pushing galaxies apart at an ever-increasing pace. The mere existence of this force suggests that Einstein's equations may require modification, or that our understanding of energy and space-time is incomplete. WMAP's data, by quantifying the dominance of dark energy, forced physicists to confront the possibility that 95% of the cosmos remains beyond our comprehension, a humbling reminder of how much we still do not know. Another cornerstone of WMAP's legacy is its role in refining the timeline of cosmic history. By pinpointing the universe's age with such accuracy, the probe provided a critical anchor for models of star and galaxy formation. The 13.77 billion-year figure aligns with the observed ages of the oldest stars and the abundance of light elements like hydrogen and helium, reinforcing the consistency of the Big Bang theory. Moreover, WMAP's measurements of the CMB's acoustic peaks allowed scientists to reconstruct the density of dark matter and baryonic matter with remarkable precision. This, in turn, informed simulations of structure formation, enabling researchers to trace how tiny quantum fluctuations in the early universe grew into the vast web of galaxies we observe today. Such insights are not merely academic, they illuminate the conditions under which life could arise, offering clues to whether we are alone in the cosmos. Yet, amid the triumphs, WMAP also uncovered anomalies that defy explanation. The so-called cold spot, a region of the CMB significantly colder than surrounding areas, has puzzled scientists for decades. While some attribute it to a supervoid, a vast expanse of underdense space, others speculate that it could be a signature of physics beyond the standard model. Could it hint at a collision with another universe in a multiverse? Or might it reveal flaws in our understanding of inflation? Similarly, the CMB's hemispheric asymmetry, a discrepancy in temperature fluctuations between opposite sides of the sky, suggests that the universe may not be as isotropic as once assumed. These anomalies serve as a tantalizing invitation to rethink the foundations of cosmology, challenging the notion that the universe adheres to simple, elegant laws. Perhaps most poignantly, WMAP's work underscores the fragility of our knowledge. The probe's data, though precise, is a snapshot of a dynamic cosmos. The universe is not static, it evolves, and our tools must evolve with it. WMAP's success demonstrated the power of observation to refine theory, yet it also highlighted the limitations of current paradigms. For instance, While the probe's findings bolstered the inflationary model, they left unresolved questions about the mechanism driving inflation itself. What caused the rapid expansion? Was it a scalar field, as proposed in many models, or some other exotic phenomenon? These gaps in understanding are not failures but invitations to deeper inquiry, a testament to the universe's capacity to surprise us. In a broader sense, WMAP's discoveries invite philosophical reflection, the realization that we inhabit a universe governed by invisible forces. Dark matter and dark energy challenges anthropocentric views of existence. It compels us to consider that the cosmos may be far stranger than we can imagine, a realm where the rules of physics are not fixed but fluid. The cold spot and other anomalies remind us that the universe is not a closed system, but a vast interconnected web of possibilities, where every observation opens new frontiers. In this context, WMAP is not just a scientific instrument, but a symbol of human curiosity, a reminder that our quest for knowledge is as boundless as the cosmos itself. As WMAP's final data transmissions echoed across the void, the scientific community turned its attention to the next chapter in the saga of cosmic exploration. The probe had set a high bar, but its successor, the Planck satellite, was poised to push the boundaries of CMB research even further. Launched in 2009 by the European Space Agency in collaboration with NASA, Planck built upon WMAP's legacy with enhanced sensitivity and resolution. Where WMAP had mapped the CMB's temperature fluctuations, Planck added the dimension of polarization, capturing the orientation of light waves imprinted during the universe's infancy. This new layer of data promised to unravel subtleties invisible to previous missions, offering a sharper glimpse into the moments immediately following the Big Bang. Planck's capabilities extended beyond mere precision. They aimed to test the limits of our current cosmological models. By measuring the CMB's polarization with unprecedented accuracy, the mission sought to detect primordial gravitational waves, ripples in space-time generated by inflation. Such a discovery would provide direct evidence for inflation, a milestone that WMAP had only indirectly supported. Additionally, Planck's data would refine our understanding of the universe's composition, potentially revealing discrepancies in the dark matter and dark energy parameters. These advancements underscored the evolving nature of cosmology, a field where each generation of instruments builds upon the last, incrementally expanding our cosmic horizons. Yet, as Planck ventured into the unknown, it carried with it the same spirit that had driven WMAP, the unyielding desire to decode the universe's deepest secrets. The transition from one mission to the next is not merely a technological leap, but a philosophical one, a reaffirmation that the cosmos will always hold mysteries waiting to be uncovered. With Planck, humanity took another step toward understanding its place in the grand design, a journey that began with the first stargazers and continues with each pulse of light from the CMB. As we peer into the data Planck returned, we are reminded that the universe is not just a backdrop for our existence, but a living, breathing entity, its story written in the fabric of space-time and waiting for us to read it. In the vast expanse of the universe, where time stretches back to an inconceivable beginning, lies a relic of the earliest moments, a faint whisper from the dawn of existence itself. This relic, known as the cosmic microwave background, CMB, is the oldest light in the universe, imprinted with the echoes of a time when the cosmos was a seething cauldron of energy and matter. For decades, scientists have sought to decode this ancient signal, peering through the veil of time to understand the universe's origins, structure, and ultimate fate. ESA's Planck satellite, launched in 2009 and operating until 2013, marked a monumental leap in this endeavor. With its unparalleled precision and sensitivity, Planck delivered the most detailed map of the CMB ever created, resolving long-standing debates while simultaneously unveiling new enigmas that challenge our understanding of the cosmos. Its mission was not merely to observe, but to illuminate the fundamental parameters of the universe, offering humanity a clearer picture of its place in the grand cosmic tapestry. Planck's journey began in the cold void of space, far from the interference of Earth's atmosphere, where it could gaze unimpeded into the depths of the universe. Equipped with state-of-the-art instruments designed to detect the faintest fluctuations in temperature across the sky, the satellite meticulously charted the CMB with a resolution and accuracy never before achieved. These fluctuations, though minuscule measured in millionths of a degree, hold the key to answering some of the most profound questions in science. How old is the universe? What is its composition? And what forces govern its evolution? By mapping these ripples in the cosmic fabric, Planck provided a snapshot of the universe as it existed just 380,000 years after the Big Bang, a time when the first atoms formed and light was finally free to travel across the cosmos. This snapshot has become one of the most important pieces of evidence supporting the standard cosmological model, a framework that describes the universe as dominated by dark energy and dark matter, with ordinary matter accounting for only a fraction of its total mass energy content. Yet, even as Planck's data reinforced the standard model, it also revealed inconsistencies. The satellite's measurements of the universe's expansion rate, for instance, diverged from those obtained through other observational techniques, sparking what has come to be known as the Hubble tension. Such discrepancies, rather than diminishing the value of Planck's work, underscore the dynamic nature of scientific inquiry. They remind us that the universe is not a static puzzle waiting to be solved, but a living, evolving entity that continually challenges our assumptions and invites deeper exploration. In this sense, Planck's legacy extends beyond its immediate findings. It serves as a bridge between what we know and what remains unknown, guiding future generations of astronomers and physicists toward new horizons of discovery. As we contemplate the results of this remarkable mission, we are reminded that the cosmos is a realm of infinite complexity, where every answer uncovered gives rise to new questions, and every observation brings us closer to unraveling the mysteries of our existence. At the heart of Planck's groundbreaking achievements lies its ability to measure the cosmic microwave background with unprecedented precision. The CMB is a nearly uniform bath of radiation that permeates all of space. But within this uniformity, there are subtle variations, tiny temperature fluctuations that reveal the seeds of structure in the early universe. These fluctuations, though infinitesimal, carry immense significance as they encode information about the universe's age, geometry, and composition. By mapping these minor differences across the entire sky, Planck provided a high-resolution snapshot of the universe in its infancy, allowing scientists to refine their understanding of the cosmos with greater accuracy than ever before. One of Planck's most notable contributions was its precise determination of the universe's age. Prior to the mission, estimates of the universe's age varied slightly due to uncertainties in measuring the expansion rate and the density of matter and energy. Planck's data narrowed this range significantly, placing the age of the universe at approximately 13.8 billion years. This figure aligns closely with previous estimates derived from observations of distant galaxies and the life cycles of stars, but the improved precision offered by Planck has helped solidify the timeline of cosmic history. Furthermore, the satellite's measurements confirm the standard cosmological model, which posits that the universe is composed of roughly 68% dark energy, 27% dark matter, and just 5% ordinary matter, the stuff that makes up stars, planets, and ourselves. This distribution, often referred to as the lambda cold dark matter, less CDM, model, remains the best fit for the observed structure of the universe, and continues to serve as the foundation for modern cosmology. However, while Planck's data reinforced many aspects of the LNCDM model, it also introduced new complexities that challenge existing assumptions. One of the most significant discrepancies arises from the so-called Hubble tension, a growing conflict between different methods of measuring the universe's expansion rate. Planck's analysis of the CMB suggests that the universe is expanding at a slower rate than expected, based on more recent observations of supernovae and other cosmic distance markers. This inconsistency has sparked intense debate among scientists, as it could indicate either a flaw in one of the measurement techniques or the presence of new physics yet to be discovered. Some researchers speculate that the Hubble tension might be explained by the existence of additional particles or fields in the early universe, such as sterile neutrinos or modifications to the behavior of dark energy over time. Others propose that the discrepancy could stem from unknown systematic errors in the data or incomplete models of cosmic structure formation. Regardless of the cause, the Hubble tension highlights the dynamic and evolving nature of cosmology, where even the most well-established theories remain subject to revision in the face of new evidence. Beyond the Hubble tension, Planck's results have deepened our understanding of the cosmic web. The vast network of galaxies, gas clouds, and dark matter that spans the universe. The satellite's maps of the CMB have allowed scientists to trace the distribution of matter in the early universe with extraordinary clarity, revealing how tiny quantum fluctuations in the primordial plasma eventually gave rise to the large-scale structures we observe today. These insights have reinforced the idea that dark matter played a critical role in shaping the universe's structure, acting as a gravitational scaffold upon which ordinary matter could coalesce into stars and galaxies. At the same time, Planck's data has provided constraints on the properties of dark energy, offering clues about whether its influence has changed over time or if it behaves differently at various scales. These investigations are essential for determining the ultimate fate of the universe, whether it will continue to expand indefinitely, collapse under its own gravity, or follow some entirely different trajectory dictated by forces yet to be understood. As scientists continue to analyze the wealth of data collected by Planck, they are uncovering new layers of complexity in the story of the cosmos. The mission has not only refined our understanding of the universe's past, but also laid the groundwork for future discoveries. By pushing the boundaries of what can be observed and measured, Planck has demonstrated the power of precision cosmology and the importance of continuing to probe the deepest recesses of the universe. Yet, as with any great scientific endeavor, the answers it provides give rise to new questions, inviting further exploration into the mysteries that still elude our grasp. The revelations brought forth by Planck's meticulous observations have not only solidified our understanding of the universe's age and composition, but have also illuminated the profound mysteries that lie at the heart of cosmology. Chief among these is the role of dark matter and dark energy, two enigmatic components that together constitute the vast majority of the universe's total mass-energy content. While Planck's data has provided compelling evidence for their existence, it has also exposed the limitations of our current models and hinted at the possibility of new physics that could reshape our understanding of reality. These unresolved questions are not mere academic curiosities. They represent the frontier of human knowledge, challenging us to think beyond the familiar frameworks of general relativity and quantum mechanics to explore the unknown forces that govern the cosmos. Dark matter, the invisible scaffolding of the universe, remains one of the most tantalizing puzzles in modern astrophysics. Although it does not interact with light or other forms of electromagnetic radiation, its gravitational influence is evident in the rotation curves of galaxies, the bending of light around massive objects, gravitational lensing, and the large-scale structure of the universe. Planck's measurements of the CMB have added another layer to this mystery by constraining the amount of dark matter present in the early universe and its role in the formation of cosmic structures. According to the LSEDM model, dark matter acted as a gravitational seed, providing the necessary framework for ordinary matter to clump together and form galaxies. However, the satellite's data has also revealed subtle anomalies that suggest deviations from this idealized scenario. For instance, certain regions of the CMB exhibit asymmetries and alignments that are difficult to reconcile with the standard model's predictions. These irregularities, while small, raise intriguing questions about the nature of dark matter itself. Could it possess properties beyond those assumed in current theories, such as interactions with other particles or a non-uniform distribution that defies the smoothness predicted by inflationary cosmology? Alternatively, might these discrepancies point to the existence of additional components, such as sterile neutrinos, hypothetical particles that interact only via gravity and the weak nuclear force? If such particles exist, they could provide a bridge between the known and the unknown, offering a glimpse into the hidden dimensions of the universe. Similarly, dark energy, the mysterious force driving the accelerated expansion of the universe, remains an enigma that defies explanation. Planck's data has reinforced the conclusion that dark energy constitutes about 68% of the universe's total energy budget, yet its nature continues to elude scientists. Is it simply Einstein's cosmological constant, a fixed value representing the inherent energy of empty space? Or is it something more dynamic, such as a scalar field, whose strength varies over time? The Hubble tension, which highlights the discrepancy between Planck's low expansion rate and other measurements, has reignited debates about the possibility of a time-varying dark energy component. If dark energy were to evolve over cosmic history, it could account for the observed differences in expansion rates and provide a mechanism for reconciling the conflicting data. However, such a hypothesis would require a fundamental rethinking of our understanding of gravity and energy, as it would imply that the laws governing the universe are not as static as previously assumed. Moreover, the existence of a dynamic dark energy field raises profound philosophical questions about the nature of time and causality. If the very fabric of space-time is changing, what does this mean for the predictability of the universe's future? These unresolved questions extend beyond the realm of dark matter and dark energy to encompass the broader implications of Planck's findings for the standard cosmological model. The satellite's data has provided a rigorous test of the MCDM framework, confirming its predictions in many respects, while also exposing potential weaknesses. For example, the observed distribution of matter in the early universe, as inferred from Planck's CMB maps, has revealed a slight preference for certain orientations and scales that deviate from the model's assumption of perfect isotropy and homogeneity. These deviations, though minor, could indicate the presence of new physical processes or interactions that are not accounted for in the current paradigm. One possible explanation is the existence of primordial magnetic fields, large-scale magnetic fields generated in the early universe that could have influenced the distribution of matter and energy. Another possibility is the influence of quantum gravitational effects, which may leave imprints on the CMB that are yet to be fully understood. These ideas, while speculative, highlight the importance of remaining open to the possibility that the universe operates according to principles that transcend our current theoretical frameworks. The search for answers to these cosmic riddles has also led scientists to consider alternative models of gravity and the fundamental forces of nature. While general relativity has been remarkably successful in describing the behavior of the universe on large scales, its inability to reconcile with quantum mechanics has prompted the development of theories such as string theory, loop quantum gravity, and modified Newtonian dynamics, MOND. Planck's data has provided a valuable testing ground for these alternative approaches, as they often make distinct predictions about the behavior of the CMB and the distribution of matter in the universe. For instance, some modified gravity theories propose that the gravitational force behaves differently at extremely large distances, which could account for the observed effects attributed to dark matter and dark energy. Similarly, models incorporating extraspatial dimensions or higher dimensional geometries offer novel explanations for the apparent acceleration of the universe's expansion. While these ideas remain controversial, they underscore the importance of exploring unconventional avenues in the quest to understand the cosmos. At the core of these scientific inquiries lies a deeper philosophical question. Are the laws of physics truly universal, or do they vary depending on the scale and context of observation? Planck's findings have forced scientists to confront this question head-on, as the satellite's data has revealed phenomena that challenge the notion of a single, immutable set of physical laws governing the universe. The Hubble tension, for example, could be interpreted as evidence of a breakdown in the consistency of physical constants over time or space. Similarly, the anomalies in the CMB suggest that the universe may not be as uniform and predictable as the standard model assumes. These possibilities, while unsettling, open the door to a more nuanced understanding of the cosmos, one that acknowledges the inherent complexity and dynamism of the natural world. Ultimately, the unresolved questions posed by Planck's discoveries serve as a reminder of the vastness of the unknown and the humility required in the pursuit of scientific truth. The universe, in all its splendor, is a realm of infinite complexity, where every answer uncovered gives rise to new mysteries. As we continue to probe the depths of space and time, we are not merely seeking to fill in the gaps of our knowledge, but to expand the very boundaries of what we consider possible. The legacy of Planck lies not only in the data it has provided, but in the inspiration it has ignited, a call to embrace the uncertainty of the cosmos and to pursue its secrets with unyielding curiosity. As we stand at the precipice of a new era in cosmology, the insights gleaned from Planck's groundbreaking work serve as both a foundation and a catalyst for the next wave of exploration. The satellite's meticulous mapping of the cosmic microwave background has pushed the boundaries of our understanding, yet it has also revealed the limitations of current observational capabilities. To resolve the lingering questions and tensions, such as the Hubble tension and the nature of dark matter and dark energy, scientists are now turning their gaze toward the next generation of missions, each designed to peer deeper into the cosmos with unprecedented precision. These future endeavors promise to unveil new layers of the universe's story, addressing the unresolved mysteries that Planck has illuminated and paving the way for transformative discoveries. One of the most anticipated projects is the Simons Observatory, a ground-based experiment currently under construction in the Atacama Desert of Chile. Scheduled to begin operations in the coming years, the observatory will combine cutting-edge telescopes and detectors to produce the most detailed maps of the CMB to date. By measuring the polarization of the CMB with extraordinary sensitivity, the Simons Observatory aims to shed light on the universe's earliest moments, including the elusive process of cosmic inflation. Additionally, it will seek to refine measurements of the Hubble constant, potentially bridging the gap between Planck's results and those derived from other methods. Similarly, the Lightbird satellite, a Japanese-led mission slated for launch in the late 2020s, will focus on detecting the faint B-mode polarization patterns in the CMB. These patterns, if found, could provide direct evidence of gravitational waves produced during inflation, offering a window into the universe's first trillionth of a second. On the horizon are also ambitious proposals for next-generation CMB experiments, such as the Cosmic Microwave Background Stage 4 (CMBS-4) project, which aims to deploy an array of advanced telescopes across the globe. CMBS-4 will push the limits of sensitivity and resolution, enabling scientists to study the distribution of matter and energy in the universe with unparalleled accuracy. These missions, along with others in development, represent a collaborative effort to overcome the constraints of current technology and to build a more comprehensive picture of the cosmos. As these instruments come online, they will not only address the unanswered questions left by Planck, but also open the door to entirely new realms of inquiry, ensuring that the quest for cosmic understanding remains as boundless as the universe itself. The universe is a vast, silent cathedral of light and shadow, where every atom, every star, every ripple in space-time whispers a story older than time itself. Among these whispers, the cosmic microwave background, CMB, a faint glow etched into the fabric of existence, holds secrets that have lingered for 13.8 billion years. It is the oldest light in the cosmos, a fossil imprint of the universe's infancy, and yet it remains a riddle wrapped in mystery. What lies hidden within the CMB's polarization patterns? What truths do its faint fluctuations conceal about the moments before recombination, when the universe was a seething plasma of energy and particles? These questions, vast and unanswerable to some, now stand at the threshold of human reach. Future experiments, armed with cutting-edge technology and boundless curiosity, seek to unravel these enigmas. Instruments like the Simons Observatory and the upcoming CMBS-4 experiment are poised to map the CMB's polarization with unprecedented precision, searching for the elusive B-mode patterns that could reveal gravitational waves from the universe's first instant, a fleeting burst of exponential expansion known as inflation. Meanwhile, 21-centimeter radio telescopes, such as those planned for the Square Kilometre Array, SKA, aim to pierce the veil of the cosmic dark ages, a time when the universe was cloaked in darkness until the first stars ignited. These endeavors are not merely scientific pursuits, they are voyages into the primordial heart of existence, where the laws of physics may have danced differently, and the seeds of galaxies were sown in a cosmic garden. To explore the CMB is to hold a mirror to the universe's birthplace. Its polarization, the subtle asymmetric distortions in its light, is a window into the forces that shaped reality. The era before recombination, when photons and matter were locked in a chaotic waltz, remains an uncharted epoch. A time when the universe was both simpler and more alien than anything we know today. Yet in this darkness there is promise, the chance to witness the birth of gravity waves, the emergence of the first luminous bodies, and perhaps even the faint traces of physics beyond our current understanding. These experiments are not just about filling gaps in data, they are about expanding the boundaries of human knowledge, reminding us that the cosmos is not a static relic, but a dynamic, evolving entity that continues to speak to us across eons. At the heart of these cosmic quests lies the polarization of the CMB, a phenomenon as delicate as it is profound. Polarization refers to the orientation of electromagnetic waves, and in the case of the CMB, it arises from the interaction of ancient photons with free electrons in the early universe. When the universe was a dense plasma, photons bounced off charged particles, scattering in all directions. As the universe cooled and electrons combined with protons to form neutral atoms during recombination, these photons were finally freed to travel unimpeded. However, the imprint of their last interactions remained, leaving behind a polarization pattern that encodes a wealth of information. Among these patterns, the B-mode polarization stands out as a particularly tantalizing clue. Unlike E-mode polarization, which resembles concentric circles, B-modes manifest as twisting, curl-like structures. These patterns are thought to be generated by two primary sources: gravitational lensing by massive cosmic structures, and the ripples of gravitational waves produced during inflation. While lensing-induced B-modes are relatively easy to measure, those from inflationary gravitational waves remain elusive, buried beneath layers of noise and competing signals. Detecting them would be akin to finding a single grain of sand on a desert dune possible, but requiring extraordinary precision. This is where projects like the Simons Observatory and CMBS-4 come into play. Located in the high-altitude deserts of Chile and Antarctica, these observatories house arrays of highly sensitive detectors designed to map the CMB's polarization with unparalleled resolution. By analyzing the faintest variations in temperature and polarization, scientists hope to isolate the faint B-mode signature of inflation. The stakes are immense. A confirmed detection would not only validate the theory of inflation, but also provide direct evidence of quantum gravity, bridging the gap between Einstein's general relativity and quantum mechanics. Conversely, if B-modes are absent or inconsistent with predictions, it could upend decades of cosmological models and force a re-evaluation of the universe's earliest moments. While the CMB offers a glimpse of the universe's youth, another frontier lies in the 21-centimeter radio signal, a spectral fingerprint of neutral hydrogen. Before the first stars formed, the universe was a dark, featureless expanse filled with hydrogen gas. As these primordial atoms absorbed and emitted radio waves at 21 centimeters, they left an imprint that, though distorted by billions of years of expansion, still echoes faintly in the present-day sky. Detecting this signal requires telescopes capable of sifting through the cacophony of galactic and terrestrial interference, a challenge that has driven the development of instruments like the Hydrogen Epoch of Reionization Array, HERA, and the future SKA. By mapping the distribution of 21-centimeter radiation over time, these telescopes could reconstruct the timeline of the cosmic dark ages and the subsequent cosmic dawn, when the first stars ignited. This would allow astronomers to observe the formation of the first galaxies, the reionization of the universe, and the interplay between dark matter and ordinary matter. Such observations would not only illuminate the universe's adolescence, but also test whether the standard model of cosmology holds true under the extreme conditions of the early cosmos. Together, these experiments represent a dual approach to cosmic discovery, one looking inward to decode the universe's birth pangs, the other gazing outward to trace the emergence of its first lights. Each project is a testament to humanity's ingenuity, a fusion of theoretical ambition and technological prowess, that transforms abstract equations into tangible data. And yet, for all their sophistication, these instruments remain humble in the face of the unknown, their success contingent on the universe's willingness to share its deepest secrets. The implications of these experiments extend far beyond the data they collect. They touch the very foundations of our understanding of reality, challenging assumptions and opening doors to realms of physics yet unexplored. If the B-mode polarization detected by CMBS-4 confirms the existence of inflationary gravitational waves, it would cement inflation as the dominant paradigm of the universe's origin. This would not only resolve the horizon and flatness problems that plagued earlier Big Bang models, but also provide a concrete link to quantum gravity, a long-sought unification of general relativity and quantum field theory. The energy scales involved in inflation, trillions of times greater than those achievable in particle accelerators, would offer insights into the behavior of space-time under conditions that predate the formation of particles themselves. Conversely, if no B-modes are found, or if their characteristics deviate from predictions, the scientific community would be forced to reconsider the entire framework of inflation. Alternative models, such as ekpyrotic universes or cyclic cosmologies, might gain traction, suggesting that the universe's birth was not a singular explosive event, but part of a recurring cycle of creation and destruction. Such a shift would require a radical reimagining of cosmic history, with profound consequences for fields ranging from astrophysics to philosophy. Even the nature of time itself might be called into question, as theories proposing multiple dimensions or nonlinear temporal structures attempt to reconcile observations with theory. Meanwhile, the study of 21-centimeter radiation promises to shed light on the cosmic dark ages, a period shrouded in mystery because it predates the formation of stars and galaxies. Current simulations suggest that dark matter played a critical role in shaping the distribution of neutral hydrogen, its gravitational pull guiding the collapse of gas clouds into the first stellar nurseries. Observations of the 21-centimeter signal could test these simulations, revealing whether dark matter behaves as predicted or exhibits properties beyond the standard model. For instance, if the signal shows unexpected absorption features or an accelerated end to the dark ages, it might indicate interactions between dark matter and baryonic matter that are currently undetected. Such findings could point to new particles or forces, expanding the standard model and deepening our understanding of the unseen architecture of the cosmos. Beyond the realm of cosmology, these experiments could also address fundamental questions in physics. The detection of primordial gravitational waves, for example, would provide empirical validation of the quantum nature of gravity, a cornerstone of any future theory of quantum gravity. Similarly, anomalies in the 21-centimeter signal might hint at the existence of exotic particles like axions or sterile neutrinos, candidates for dark matter, whose interactions with ordinary matter remain elusive. These discoveries would not only refine our models of the universe, but also inspire new technologies, from advanced materials science to novel approaches to energy storage and computation. Perhaps most profoundly, these efforts underscore the CMB's role as a bridge between the known and the unknown. Far from being a static relic, the CMB is a dynamic archive. Its patterns are palimpsest of events that shape the cosmos. Every photon that reaches our detectors carries the weight of history, a record of collisions, expansions, and transformations that occurred in a universe vastly different from our own. By decoding this record, we are not merely observing the past, we are engaging in a dialogue with it, asking questions that transcend time and space. In doing so, we affirm the enduring power of human curiosity, the drive to seek meaning in the void and find order in the chaos. As we stand on the precipice of these discoveries, it becomes clear that the universe is not a closed book, but an open manuscript. Its pages waiting to be turned by the hands of those who dare to ask, what comes next? The CMB's polarization and the 21-centimeter signal are but the first chapters in a saga of cosmic revelation, each observation a thread in the intricate tapestry of existence. Yet, for all the progress made, the universe remains a realm of infinite complexity, its depths unfathomable even as we strive to map them. The next segment invites us to turn our gaze toward the stars themselves, not merely as distant points of light, but as laboratories of transformation, crucibles, where the elements of life are forged. Here we will explore the life cycles of stars, the alchemy of supernovae, and the role of stellar nurseries in seeding the galaxy with the building blocks of planets. Just as the CMB reveals the universe's infancy, the life stories of stars will illuminate the processes that shape the cosmos on scales, both intimate and grand. From the death throes of massive stars to the quiet persistence of red dwarfs, this journey will reveal how the universe recycles its raw materials, weaving the same atoms into new forms across eons. For now, let us linger in the quiet wonder of what lies ahead. The tools of tomorrow, whether orbiting satellites or radio arrays nestled in the cold silence of Antarctica, are not mere machines. They are extensions of our collective yearning to understand. They are the instruments of a species that looks up and sees not an empty sky, but a canvas of possibilities. Each pixel of light a question waiting to be answered. As we prepare to delve into the lives of stars, we carry with us the lessons of the CMB, that even in darkness there is light, in the void there is structure, and in the unknown there is always the promise of discovery.